the necessity of combining HPC and quantum computing. And we are now also shifting from a hardware market to a software market, just like a classical IT. So the big money lies in the software, not really in the computers that run it. So Intel is large, but Google is 10 times bigger. And the value of quantum computing has been estimated by several instances, but one really sees it now that it will be a really huge business in the medium term. And that's also why HPC centers are already now investing time and effort into making this a reality. Here I just highlight some of the challenges and the differences when you compare quantum computing to classical supercomputing. And the first one is really problem identification, because we know that we cannot solve everything in a quantum computer. So really, the first step is to figure out what exactly a quantum computer should compute. And this is not trivial at all. Really fitting in a real-world problem into parts that a quantum computer can be useful for is highly non-trivial. And after this, then we need to program them, and that's of course a completely different paradigm compared to classical programming, as we heard yesterday in the algorithms session. And at the same time, we just have to realize that for a very long time still we are going to need to work around the limitations like noise and qubit connectivity, decoherence, and so forth. Programming now and just assuming that at some point we will have completely fault-tolerant ideal qubits and quantum computers, I think is not the way to go. We have to realize that we will have decoherence with us for the foreseeable future. And then, of course, as was already mentioned as well by many speakers, all quantum computers are different. So it means that the same program will produce different results on different hardware. From the user perspective, this means that we really need to give our users access to several different quantum computers. Here's what we have been doing around LUMI. So last year in March, we connected actually the LUMI supercomputer in Finland to the Wallenberg Center Swedish quantum computer and run the successful cross-border quantum job where we connected classical resources on LUMI and the quantum resources on Cal 9000. In May last year, we did the same for connecting LUMI with the Helmi quantum computer, which is the Finnish quantum computer co-built by IQM and VTT, the State Research Center. And here we then also integrated it fully with all the standard resources from an HPC center, so identity management, resource allocation, and everything else. And the next step is then to implement this LUMI-Q concept, which means that we want to set up really a global distributed HPC plus NQC, where N stands for that we really want to connect several quantum computers now with the HPC centers. This is now starting the project from a European perspective, but we really want to, of course, in the long term to make this a global network and a global collaboration. And here a key component is again the software, and especially the software stack for the middleware, where we really need to work a lot on getting an efficient connection between HPC supercomputers and quantum computers. Here's a bit more about the LUMI-Q concept. So it's a project. It's one of the 6 projects that now this year will start working on integrating quantum computers with supercomputers within the Euro HPC framework in Europe. So it builds already on the 10-country LUMI consortium, but then we also have new members, the Netherlands and Germany, or representatives from Germany. It's of course not entire countries that are part of consortium. But here the idea is that this is a really diverse selection of resources that we will be able to provide to our customers through this. So within this LUMI-Q project, we will from the onset integrate 5 different quantum computers around Europe to 3 different supercomputers around Europe. So we have the Helmi computer here in Finland, the Cal 9000 in Sweden, and then we have the two quantum computers from TNO/SURF/Delft in the Netherlands, and then we will have a new quantum computer that we will procure within this project that will be located in the Czech Republic next to the Carolina supercomputer. But we want to build this up really as a unified software stack where all of these can be accessed in the same way no matter where you sit in these consortia countries and in the whole of Europe, because it's a Euro HPC project. Okay, there was a bit of talk of this on-premise integration of HPC computers. So just to give a bit of background, so there's 3 different ways of connecting HPC and QC, and they come with increasing level of complexity of the software stack that you need to have these. And the first simple one is the standalone one, which also can be called cloud access, where you just connect it somehow over the internet to the HPC center here, represented by the blue server boxes. And then you have the on-premise or co-located approach, where you just put the quantum computer next to the HPC system. Or then you can build up this distributed way that we are going for now in LumiQ, which is it's a combination of the distributed and co-located. But here the QPU and the HPC resources will be physically distant, but we will still have a classical resource next to the quantum computer, and that is the main point here. Note on latency and these hybrid algorithms. Hybrid algorithms will be the ones that people will be running on quantum computers in the near term. So we have this tight loop here in the middle between the purple and the blue box, where we have a quantum part and a classical block. And when both the classical block and the quantum block are fast, then the communication here in between these has to be even faster. Otherwise, we get latency bottlenecks. And with the QPUs as they are today, they crash. The coherence time is so short that they crash very quickly. The quantum block has to be fast. This also means that the complexity of the problem that we are running there is very small. So also the classical optimization part there will be very fast. So now in the near term, these hybrid algorithms will require very low latency. This means that this standalone approach creates too much overhead. So we cannot have a system like this where we would have a medium to high latency to run hybrid algorithms. So we need to have this classical processing physically close to the QPU, and the idea there is that this physically close classical resource just keeps feeding the QPU with new input. But here the crucial thing is that this is not an HPC task. We don't need a supercomputer to keep feeding the quantum computer with anything for the moment. And probably not for a very long time. It's enough to have a powerful server, this orange box close to there, which then in itself communicates to the HPC system. And this is the distributed model that we are setting up, for example, in the LumiQ approach, and Nordic West and others that CSC is involved in. And we want to do this because when we have this software stack, efficient software stack in place, it's very easy to add additional quantum computing resources in a plug-and-play manner. So, because then we only need to install one classical server next to the quantum computer and install the software stack that we have built. This really increases diversity and inclusiveness, because now it really becomes easy to also collaborate and share quantum computing resources between countries, between institutes, and so forth. And for the end users, this is highly beneficial, because immediately the end users will get access to a much larger selection of quantum computers than they would if they would just rely on the quantum computers installed in one specific HPC center, for example. And this facilitates then, of course, also time sharing of QPU resources with partners. And another point is really this, that now the quantum computer and the supercomputer can be optimally located when they are separated. So we need to have HPCs in large data centers. And here the main point is that the data center needs sufficient and affordable electric power. For example, by placing it sufficiently high up north. But quantum computers, again, don't really need any power at all. So they run with the tens of kilowatts. But they do need shielded environments to shield them from the temperature, vibrations, and other noise sources. And And then one of these other noise sources is actually cosmic radiation, which already now is starting to affect quantum computer operations. This might mean that we need to put quantum computers in the future underground. And there's not that many data centers that are located underground, so it really might become a problem to have them co-located because of the very different needs in environment that quantum computers and supercomputers have. Okay, just a very brief note on the Lumi-Helmi pilot phase. So we have now opened it for all academic users in Finland, and we have already several projects running on this. And this is, I think, very important because then we get a feel for what is it that our customers actually want out of a HPC and QC environment. Instead of trying to guess what our customers need and then build around that, really having this direct discussion, continuous discussion with the end users, I think is very important because we are still at a very early stage with quantum computing, and we need to listen to the needs of our customers, the end users, so that we really can provide a service that is useful as early as possible. And then I just want to finish with this, that quantum computing really is a multidisciplinary problem. If you want to get any sort of quantum advantage, no matter how you measure it, we really need to get all experts in the same table or around the same table. And here, really, we need to remember, I emphasize here, the end users. Just so that we don't, as engineering backgrounds, try to build something that actually no one really wants. There is a risk for this, and that's I think we have learned that from previous generations of trying to provide new services. But I think in the case of quantum, it's really important to keep this in mind. And with this, I'll end and thank you for your attention.
Thank you so much, sir. The house is open for the questions, if any.
Hello, Mikhail. Colonel Nath here, Executive Director, C-DAC Pune. Can you tell us, I think that's a very good approach that you have a classical powerful server next to the quantum computer and linked over the long distance to the HPC, which can be far away. So have you developed some sort of a software stack or the middleware to communicate with the quantum computer?
Yes, it's under development, and much of the development will also take place now in this LumiQ project once it starts. But so far it's been mostly setting up what we need and also defining the protocols of how we need to do this. And now really we are starting to set up this, but it is in very early stages, a bit similar to what LRZ is doing, and we are actually our friends in LRZ have very, in many cases, see the world in the same way as us. But there is lots of rooms to play around with still, and play around maybe sounds like wrong, but there is, we need to implement this in real life to see where the new bottlenecks arise. So, but the first stage, I think, is to really define the problem properly and see where problems could come up, and then implementing the software stack. But there is plenty of work to do for certain.
So are Helmi and Lumi linked up in the same configuration which you're talking about?
No, that's Helmi still doesn't have this powerful classical server next to it.
Okay.
So that is the next step. So for the moment, it is a rather loose connection. It's fully integrated with the HPC, but we have the latency problem there. Although actually it's not really a problem because anything you run on the quantum computer now anyway takes longer than the communications between them, and that actually will stay for a long time, because if we actually think of when a quantum computer becomes useful, then also the calculations on it will take on the order of seconds at least, and then all latency problems are completely gone.
So you
because the communication
linked up on a dark fiber or something like that, or it's on the internet?
No, it's actually for the moment it's just over the normal internet, and we don't see actually any reason to change that, except if we want to do some really sensitive data processing, then we can find out other solutions. But for just standard calculations, scientific calculations, and even commercial calculations where standard encryption is sufficient, because it is an encrypted line, of course, but it runs over the normal high-speed fiber network.
Thank you. Thank you.
I have one question here regarding the connectivity between the HPC and your quantum computer. Right now, people are using Ethernet. That is actually high latency, low throughput network. So, what do you see in the future? What kind of network will be there between the HPC and the quantum computer?
It depends a bit on how the use cases develop. I think internet will actually be sufficient for a long time because the data intensivity is very low. If you just think of it, even with the 1,000-qubit quantum computers, then the data that you read out of there just from a single shot, so that 1 kilobyte of data. So there's not actually that much data moving around. The big problem can be latency. If you are actually going to at some point need true real-time HPC processing of the output of, for example, from a quantum computer, and this might be the case if you really want to do real-time error mitigation, for example, and then latency will become a problem. You cannot really do anything about that if because there is a limit on the speed of light. So then in that case, then it might become required that you have a sufficiently powerful HPC resources co-located with the quantum computer. But for the foreseeable future, that will not be the case.
Okay. Thank you.
Thank you so much, sir. Now let us proceed to the panel discussion. With the permission of the session chair, I would like to call Mrs. R. Rajminakshi, C-DAC Pune, Dr. Gurmohan Singh, C-DAC Mohali, Dr. Aswija B., C-DAC Bangalore, Mr. Vivek Nanwal, C-DAC Hyderabad, Mr. Samrit Maiti, C-DAC Pune, and Mr. Amit Saxena, C-DAC Pune. I request the session chair to take forward the session for the panel discussion.
Good afternoon, all. I think this is the last session before lunch, and I think we have to wrap it up slightly faster. And we have about 6 people in the panel. So in this session, in the previous session, expert talks from Ms. Laura LRZ and Dr. Michael from CST IT Center. They have already given very good view on what kind of HPC integration, HPC and quantum computer integration issues are there, what are the challenges, and what kind of developments are happening. So the challenges are like what kind of hardware interfaces has to be there between the HPC machine and the quantum computer. Then what kind of software development environments are supposed to be there to have this kind of hybrid applications developments. And what kind of use cases of hybrid applications are there, and as well as what kind of system softwares which will be required for resource sharing of this kind of HPC hybrid computing, like scheduling of the jobs and so on. So in this session, we have 6 people, Mr. Ashwajit B., Mr. Vivek Nainwal, and Mrs. Raj Minakshi, and Dr. Gurmohan Singh, Mr. Samrit Maiti, and Mr. Amit Saxena. So since we have very limited time, I am giving maximum 5 minutes. If you can finish before that, that will be good. To start with, we can start with Mr. Ashwija B. Ashwija. Yeah, she is there. Achha, you are there. Sorry.
Thank you. So I have been asked to speak on the challenges in developing the software stack for the quantum computing systems as such. So having seen all the complexities involved in developing the hardware, all these sessions that we have heard till now, I mean, it might be intriguing to look at what kind of software will be required for making these systems operational. And looking at the heterogeneity of the various hardware platforms that have been discussed, you might make a guess that developing software is equally challenging for making these kind of systems operational, right? So we'll just try to, I mean, as part of my talk now, I'll just try to enlist some of the challenges which, of course, most of us over here, we all know that it is quite challenging. We'll just try to formally enlist for the benefit of the proceedings of the symposium over here. So one of the major challenges, which was of course highlighted in the yesterday's session also, comes from the design of the algorithms as such, right? I mean, once you have these systems available, what kind of applications, even in the previous sessions we talked about, do we have some killer applications which could demonstrate the usability of these hybrid systems, or the kind of effort that it is going for building these complex quantum computing systems, right? So one of the challenging tasks is again on the algorithm design aspects, right? So apart from what we call as seminal algorithms in the domain of quantum computing, be it the Shor's algorithm or the Grover's or the Fourier transform as such, we really have a handful of algorithms, quantum algorithms as such, right? So we really need to put a lot of effort in the space of algorithm design as such. And of course, design of these algorithms is again not so trivial, which is quite understanding. I mean, someone has to think quantum if you have to come up with a quantum algorithm as such, right? And what we are trying, I mean, if you think from the classical perspective, what we are trying to address is to come up with an algorithm that can solve some problems with the complexity of NP complete level or even NP hard, right? So we are actually targeting something which is not being achieved in the classical level. So that actually stems, contributes to the challenge of designing these algorithms. And of course, designing a quantum algorithm, of course, you will have to think quantum, and you will have to orchestrate interference in some way, because we are dealing with probabilistic systems there. Take the example of Grover's algorithm itself. I mean, the fundamental concepts of quantum mechanics have to be harnessed in order to come with the best results of any particular execution as such. So you will have to orchestrate interference in some way to do something called as an amplitude amplification, so that you get the best desired results when you try to run the experiments on a probabilistic machine like a quantum computing system as such. Okay, and other than that, of course, if we are talking about developing the software for the near-term systems, we do have challenges in developing the control software as such. People have been speaking about developing the control electronics, which is again a challenging task as such, wherein you have multitude of different implementations and you need control electronics for controlling all of this. Definitely, you need the corresponding software parts which can help in operating these systems, or what we can, if you can draw an analogy to the classical systems, what we call as device drivers, right? I mean, you need to write these low-level software components which will interact with the hardware as such at the very lowest level, if you consider the software stack as such.
One more minute.
Yeah, sure. I'll try to wind up. And of course, if you're talking about having the hybrid systems in place, then you also have the challenge of designing the runtime. So what is a runtime? Something similar to what we have in terms of GPUs. We have something called as the CUDA runtime, which basically helps you to execute the program or transition from the main CPU to the GPU. So now you have the complexity of having a gateway wherein you are trying to move the data from the classical to the quantum. So do you have to develop some kind of quantum gateways which will help you in this kind of transition? So this is all part of the bigger runtime challenge. And of course the compilers, which I already mentioned in some way, like since there are multiple platforms available, multiple processor architectures available, be it superconducting or photonics, whatever it is. And above all this, we also have different quantum processing paradigms by themselves, right? I mean, you have these quantum annealers, you have gate-based quantum systems, and multiple other quantum systems like measurement-based quantum computing devices or fusion-based quantum devices. So even if you have to give programmability if you want to have software which will enable the programmability of all these systems, then you will have to work at how a high-level definition from the programmer could be translated into these different architectures. So these are some of the challenges which I would like to highlight from the software stack as such. Thank you.
Yeah, our next speaker is Vivek Nainwal.
A very good afternoon to all of you. So what I'll try to tell is, we had an experience with the QSIM. So first I'll tell what is QSIM. It is one of the projects under which an indigenous simulator was built in collaboration with IISc, IIT Roorkee and C-DAC, and it was one of the foremost projects that C-DAC had taken up in the domain of quantum systems and quantum computing specifically. And while this project seeded up in IISc and all, and the simulator was built. Now the main challenge is how to take up the simulator and put it across the web or cloud infrastructure so that people can be benefited from it. So the first thing was that, and to understand that, we had a wonderful cloud computing team who built up the whole stack over it and made it available onto it. And the next thing was, when the simulator was built, it needed to be optimized actually. So optimized in the sense, instead of running onto the server, we wanted to make it available onto an HPC infrastructure so that it can use multiple cores, it can be run onto the GPUs and all. So that thing had to be customized, and the basic algorithm that was built inside the simulator had to be tweaked, and most of the part of the algorithms have to be found out, which can be parallelized, which can be ported over onto the GPU, whether we can use single GPUs or not, whether it is possible to run those portion on multiple GPUs, whether over multiple node it is possible or not. So those kind of challenges we had faced. Initially we provided it for the CPU cores, and we did, and we identified the areas which need modification. Then we parallelized over HPC. So an integration of your quantum simulator to the HPC infrastructure was also made. So right now this is also available to everyone. So anyone who wants to use this particular simulator just need to throw us an email. We usually give them an access and they can run their simulation. The simulation, the backend is actually configured to Param Shakti machine. So all your simulations are sent back to the Param Shakti machine where it is run, and the result is given back to the user. So there is a workbench that was also developed by the team around this simulator to make it more usable. So that is the whole thing. In quantum computing, if you can give a very nice user interface and easily people can try out the experimental stack or the software, and then you can always make improvement over it. So with the feedback given from the user, specifically we used to take feedback and integrate it back onto our site. So that was one thing we always kept in mind.
Are also in focus in the commercial sector, basically on the finance, transport, then on the aerospace basically. So looking at this space, when we choose, we need to identify the ones which are very much specific and that can cater to the needs of the user. So usability and the reliability plays a major role when we identify those applications. So looking at at the health, basically I come from the health background, so looking at the health, so we have lot of use cases that can be thought of, ranging from the medical imaging where you can perform a lot of operations in no time. And we wanted to optimize on the surgery planning where the accuracy plays a very important role because we cater to the individualized patient treatments. So now the bridge comes where we have the our classical computing and then the quantum computation. So is it possible, how are we going to bridge this gap from translating a classical problem into an equivalent quantum state and then the circuit and then get back the result and porting it back onto the classical systems? So once we bridge this gap, we will be able to take the solution to the user and to the market. So we have a plenty of use cases. We have identified set of use cases, and then we also have the quantum simulators where we can simulate some of the algorithms. So now we need to try out lot of algorithms and the things which are available in this particular space. When I look into the algorithms for implementation, I could divide them in three spaces, basically in simulation and modeling. We have it in the optimization space and then in the machine learning. So whatever we do it in the classical machine learning, we almost have it in the quantum space as well. But one thing what is required is the repetitive simulation and then see how we are going to take it forward in the implementation space.
Thank you.
And we also have few challenges, just one more second. So we also have some challenges in the data representation, because when I look into the imaging, when this is an information era where we have lot of data coming from different data types. Basically we have videos, sounds, your text, and then the images. So how are we going to translate or represent them in the quantum circuits or the quantum state for further processing so that it can be easily done? So this is one of the challenge I see. Thank you.
Thank you, Rajminakshi. Next one is Dr. Gurmohan.
Good afternoon, everyone. Hello. Hello. Yes. Good afternoon, everyone. So from yesterday we are listening that quantum computing has a lot of use cases, and quantum machine learning is emerging as one of the topmost use cases of quantum computing. So in quantum machine learning, I think it is the next big thing which is going in quantum applications. Please move my next slide. Okay. So we are saying that with ever-growing amount of data, so as per an report, due to emergence of technologies like IoT, cloud computing, and then wireless sensor networks, and social media, a lot of data is being generated. And as per an report, there is an increase in data size by 20% every year. So to handle that amount of data, you need to scale up your classical systems, or you have to move to some other kind of computing paradigm. So in that sense, quantum computing can help us a lot in that particular thing. So quantum computing has a lot of impact in addressing various problems in life sciences, chemistry, material science, cybersecurity, and optimization kind of applications. So basically nowadays, quantum machine learning is basically used for clustering, classification, and pattern finding kind of applications. Please move next slide. So these are the futuristic applications of quantum computing, or we can say quantum machine learning can also be used in many of these applications. So in life sciences, we can use it in drug discovery, clinical development, then diagnostics, therapies. Then in cybersecurity, I think biggest use case or application nowadays we are having is classification of malwares. Or we can say next we could have ransomware detection. So in finance sector, we are having a lot of we can say applications like trading, targeting and prediction, risk profiling, then portfolio management kind of things. Please move next. So from this, we can say that quantum machine learning is emerging in a very good field, and it is providing us solutions to many of the complex problems. So how it is providing basically solutions? Because in quantum computing, we use principles of superposition and entanglement, and these two principles provide us the power to handle multiple states simultaneously. So this is a major advantage we can gain from the quantum machine learning in these kind of applications. So nowadays the focus applications and areas of quantum machine learning are hybrid quantum machine learning with heterogeneous quantum devices and variational quantum circuits and collaborative things. So I feel that at present, whatever kind of resources we are having, so this is the one use case that we can start straightway working on. Thank you.
Thank you, Dr. Guruman. Next one is a team, Mr. Samrit Maiti and Mr. Amit Saxena. Yeah.
Yes, okay. So our topic is integrated HPC and quantum platform. So, and myself and my friend Samrit, we both will be talking together on this topic. So we are hearing about this since Laura has already told about LRZ Center. A lot of efforts are in the supercomputing center are going on. So our chair had a question that what are the challenges? So I want to just show this slide that we are a supercomputing center and our chair himself is an expert in the HPC. Since C-DAC is working in HPC since I think more than 25 years, and Param series of supercomputer are being done by C-DAC. Now we have already integrated, as Abari sir told, that AI has been integrated, big data has been integrated. Now is the turn of the quantum. So now we have a challenge in front of us that we have designed a Param-Q quantum computer concept, and I think we should thank to Manoj ji, who has designed a very good, excellent, and it seems to be realistic, but this is a architecture that we have to build this Param-Q for the C-DAC. Now the challenges that we can see is the arrow in between. That arrow in between we have capped that requires softwares, libraries, interconnect, and then the job management type of thing. Like Slurm is in job management that is doing this in the HPC, but how that can offload the job to the Param. So this can be used as an accelerator. So what we are planning here is that there is an HPC well-established system where Raj Meenakshi madam told about that we have use cases already working on the HPC, and we have strength in HPC. Now there is some part of the HPC that requires huge computation challenges. Mostly it is optimization part, and the quantum computers are good in optimization part. So can we offload that part only to the quantum computer, and they can behave as an accelerators, and then they can give the result back, and the result can be combined classically, and then the final results can be given. So this is the whole concept we want to try as an HPC quantum integration. Now there are, SVJ covered about the software, libraries, madam covered about the use cases, and then machine learning, then we have hybrid algorithms, those aspects. And then QSIM can be integrated. We are also trying with like GPU, vector cards, FPGAs. Those cards we can try starting, and then we can offload some part to them, and then we will try the quantum computer. Now my friend Samrit will add about this thing.
Thank you, Amit. Most of other panelists has covered the major challenges at this point of a time to integrate quantum and HPC system. I would try to give a holistic view as I'm standing in between your lunch and you, so I would not take much time. Just touch upon the points holistically. Initially, basic sciences has used HPC as the accelerator to simulate the thing, which was not quite possible because of many reasons. It was not possible to experiment in real lab, so they tried to use HPC system as their accelerator for the science and advancement. And that is what successfully HPC has always done. The basic sciences has progressed because of HPC. Now, after a certain point of a time, because of certain limitations, HPC started to look forward to more performance. And then the emergence of various architectures, including GPU, came into play. At this point of a time, another turning point or another major need has came up in HPC, where HPC is looking forward to quantum computing as another major big accelerator. So this is what, when you consider end user point of view of an HPC, end user point of view, all of them are looking forward to quantum as another accelerator. So from that point of view, I can tell you there are majorly 4 verticals where all the experts from different domain has to look into and then start working upon holistically. And C-DAC also has to participate into all of these things. First of all, computer architecture, when we talk about, now here in this case, we would be talking about quantum architecture. There are various basic science advancement has happened, gate-based quantum computing and many other type of quantum computing, and they're coming up. Now the major challenges here is, this is a different kind of computations. And HPC, when I consider computer architecture, HPC has considered its computing in a completely different category. How do we create a bridge between these two kind of architecture? So from architecture point of view, we have to bridge the gap, that is one point. Then comes the computer organizations. How both of these two category of computer systems or computing systems can be organized. They can be co-located, they can be connected over cloud, or a quantum accelerator, miniature form of it can be integrated inside an HPC node. This is called tightly integrations of an accelerator in HPC. So this is called organization, computer organization oriented challenges. Then comes middleware challenges, where we would be looking forward to a very, very comfortable runtime. From end user point of view, we are not much concerned, or rather we would not like to go into the complexities of quantum computing when we are looking forward to use it for our application development. There, we require a very mature, stable, and comfortable runtime, where an OS, which is quantum aware, is a very much need of this time. Now, the last point I would like to mention is, now quantum technology, as it is coming up, participate strongly to develop the libraries that they are going to use in future. So this is the 4 vertical I wanted to pinpoint. What immediate goal or target that C-DAC can target upon is this particular time quantum experts and HPC experts to come together and participate in all activities where we can create success stories as early as possible domain. Thank you very much.
Thank you, Samrit. Any questions? Yeah.
Regarding that earlier expert talks also, we were just seeing that the interface between HPC system and the quantum computer. Like currently it is Ethernet. So in future, like which has the latency and other issues. Okay, so in future, like see, maybe we have to standardize that, like see, which should be like less latency, and also like see, when we will be moving to the next, I don't know, like it could be the new interconnect itself, so that the HPC, the main processor itself also has to evolve, so that it has to provide the proper support of the whatever the upcoming new interconnects and all, like whatever has happened in case of, like if we see all the accelerators, like we have moved that, okay, all the accelerators are now going toward the CXL, the unified interconnect technology. So maybe for the quantum computers also, when we will be integrating it together with the HPC, we have to think of like see maybe some standard interconnect, and accordingly that same interconnect has to be in the main HPC processor also.
Yeah, I think that is a very nice suggestion, and I think we had some initial discussion with the IQM. Their team, I think George was working with, they were saying that PCI Express based interfaces they are trying to develop. in the quantum part. Now, when we talk about the InfiniBand and that connection, so we have to bridge that layer, and then one of the close, tightly coupled network has to be provided so that the job submission and job execution latency is very less. So that work is going on, I think, in most of these things. Thank you.
Thank you, everyone. I request them to be remain seated, and I request the session chair. Now I request Colonel Lekinath to felicitate the session chair, Mr. Sanjay Vandekar. Thank you all. With this, we conclude the session. We now break for lunch. The next session will begin at 3 o'clock. Meanwhile, the participants are requested to visit the stalls exhibit from our industry partners, where various work in the area of quantum computing is showcased. Thank you.
Okay. Good afternoon, everyone. I request everyone to please kindly be seated. Welcome back. I will take you through the next session, that is valedictory session. The session is chaired by Colonel Ekinath, Executive Director, Corporate Strategy and C-DAC Pune. I would like to call Professor Kailas Rustugi, ex-head RRCAT Indore, Professor Arvind, Dean R&D, ISO Mohali and Vice Chancellor, Punjabi University, Dr. Mamta Khaneja, Scientist F, SSPL, DRDO, Dr. Santu Sardar, Director, DYSL QT, Dr. Sangeeta Maini, CEO, iHub QTF Pune, Dr. Harish Sahu, SAG, DRDO, Dr. VR Chele, Director, Quantum Technology, DOT, Professor Anil Prabhakar, IIT Madras, Mr. Manikandan K, Bureau of Indian Standards, Mr. Ashish Chudasama, Business Finland, Dr. Gautam Paul, ISI Kolkata, Dr. Prabhakar Krishnan, Amrita University, Mr. Sujoy Chakravarti, Confluence, Professor Monica Agarwal, Co-founder, Q Krishi, Quantum Private Limited, Dr. J.D. Daya Pradhan, and Dr. Nitish Kumar Das, Variable Energy Cyclotron Center, Kolkata, Mr. Pradeep Kumar, Director, Qubit Labs Private Limited, Mr. Sunil Gupta, Co-founder and CEO, QNU Labs Private Limited. I request all of them to please be on dais.
Yeah. Please come up, whoever is physically present, and can you show the people who have joined online so that we can have a look at all of them? Yes, we have a sizable number of panelists with us to start the valedictory. In fact, I pushed the valedictory just after lunch so that any of you who have flights to catch or something can also attend the valedictory session, because it's a very important session for us in the sense that generally valedictories are towards the end and things get diluted and generally a lot of attendees go away and I didn't want that kind of a thing to happen, because what I want to emerge from this session is your views, your candid views about how we as a nation should chart our roadmap ahead in the quantum computing arena. So there are certain questions I have shared with you. Those questions will be flashed on the screen, and you have the liberty to choose any two questions and speak about them, your views, and some people who have some divergent views can contest. But I would definitely like detailed comments, because we cannot have everybody's comments in the limited time available about all the questions. So kindly, we would look forward to your detailed comments on email directly to me or SQC, whichever is our email alias we have for the conference. But before we start the valedictory session, I want to start it in a very unusual way. I want to actually, in your presence, felicitate my organizational team in front of you. So please come up, the entire team which has been working relentlessly in organizing this event, and please show yourself to the audience. So we have had, this event rigged up in a very, very short time, and all of them have helped. In fact, there are so many of them, probably there are more than the audience. So, but they all have played the role. And right from when we started Anindita has taken real pains to identify the people, because the mandate given was that we must have the structure given to the first I wanted to call it a conclave. She said, no, conclave becomes too technical, so you call it a symposium. So we had a symposium. And then all the people who are working in different areas, which are forming the subsystems of a commercial quantum computing system. So these sessions were crafted under those, and it was a very, very humongous task to identify the people working in different areas in the country. And she did the job well, and knitted a very intricate web, invited them, people from abroad, and everyone, organizing the timings, the keynotes to suit timings of the people from abroad. And I think it's a wonderful job. Well done, Anindita. Well done. And along with that, our team who has been looking after the arrangements here, picking up the right people, because the audio, video, and the quality of everything, the video rendition, and nothing has failed. I'm really glad. So, going to the right vendor and getting the right things. And our IT resource management team, which has been sitting behind, and it's not very evident to you, but they've been, doing a lot of juggling in getting the people in the forefront when they're speaking, getting their presentations so that it could be read, and switching on, switching off the mics so that there couldn't be any echoes, and a lot of things they have done. So I think Swaroop, under him, where is Swaroop? Yeah. So the wonderful job done by your team. And then we have our team under Manojji, who has designed all the backdrops and so many other things. So I think he's been a genius in designing the backdrop. Where is Manoj? He has been hiding behind. Wonderful. The invitations and the entire admin under invitations have been done by my office. So Nilima and Sunena and the other people involved, Deepu. So wonderful job done. Pomnikar, who's been heading the admin team, under him the transportation, the the accommodation, and all those arrangements have been done. A wonderful job done. And of course, Madhvi and our new canteen manager who has come, the food part has been looked after by them very well. So, great. So thank you so much for your generous applause and encouraging this team. Thank you. Anyone who has left out? Yes. Okay, great, Vivek. So we have a special interest group in C-DAC, and people have come from all over our C-DAC centers. So great applause to them also. They have helped us in organizing, being session coordinators, and yeah, I forgot about them. Thanks for reminding me, Anindita. And anyone else whom I have forgotten? Yes. Yeah. Great, Aditya. All the people, yeah, all the session chairs, the compares, yeah, under Manoj, yeah, Amit Saxena, yes. Amit, he has done all the arrangements here, gone and selected the right kind of people so that they could provide the right kind of ambience. So thank you so much. And to all those who probably still are left out, my apologies, but my thanks and gratitude to all of them. Thank you very much. So you can have your seat. Yeah, we can have a photograph. Thank you. Yeah. Thank you. Thanks. So now we start the session. Please, let's get down to some serious business so we could display the list of questions, and we can start, I think, from the online attendees. Yeah. So anyone who's online can address any two questions and give us your views.
Hi. So I'm Professor Monica from IIT Delhi. So can I start on this?
Hello. Yeah, please go ahead. Please.
Yeah. Yeah. Thanks a lot for this wonderful opportunity and for this wonderful session that has been organized by C-DAC on this high-tech technology, which is kind of the what I should say the need of the time. I also would like to thank Dr. Anandita, as has been correctly said. She has taken a pain and has contacted every one of us personally, and that personal touch that she has given to this symposium has given it a different flavor. Uh, I actually want to say two things about the quantum. And as we all know, this quantum is kind of a new thing and has many potential and has potential to solve many problems. And for Indians, we are also looking into it. As India stands way ahead with the artificial intelligence, it has established itself. India should also become a world leader with the quantum technologies with the year to come. We need a good manpower and we need good training on that. Apart from that, what I feel is the most pressing thing in the quantum is the quantum qubit state. It's still very noisy, and people are working on ways to handle that quantum error correction or quantum topography, whatever, or the possibilities of it. That is the most pressing thing. What I feel is in the success of the quantum at present, and what I feel today is almost, I think, the way people might have felt at the invention of the vacuum tube, and that time they might not have thought that this vacuum tube will be resulting into the mobile phone or the laptop which we are using like way back in 1945. So similarly, we are also on a new era. What I feel is that we should move in a very cohesive way and in a very cautious way so that we can use its advantage in this best possible way, and with a basic understanding and a basic research on it. We should not
Thank
jump
you.
on the many things, and yeah. So that's what
Yeah,
I
thanks. I
wanted to
think
say. Yeah,
you're
thank
right.
you. Thanks a lot.
We should encourage all the R&D which is going on. We don't know at what time which kind of technology might find favor and might overtake the others in by way of scaling or so many other things, the error correction and so many things. So that's a point taken. Thank you very much. So we have a hand there. Sorry, who's raised his hand? I cannot. Kailash ji. Yeah, yeah. Dr. Kailash.
Yes, please.
Yes, please. Please go ahead.
Yeah, I have a few things to say which are quite specific. First is that there is a background to this meeting, and that is that a quantum-enabled science and technology program was launched by DST some 3-4 years ago, and many of the things that you see today happening are as a result of that. So I want to take you through that background in a minute. Just all related to quantum computing. Other parts I'm not discussing here. So what are the outcomes of that program? And before that, I should say how things have been changing. See, in Bhopal, we had a meeting in 2018, and we were very ambitiously looking at 4 or 5 qubits discussion. By now, that we have exceeded in superconducting qubits. there is some progress in the Professor Chandrasekhar and Professor Das have presented their views on quantum integrated quantum optics, photonics based systems. NPL project has not made so much progress, but we had started some single photon detector development. Bhalmudi and Kasturi Saha were funded for diamond systems. They have also made progress. And single atom, cold atom qubits were also funded. This has been somewhat slow, and the reasons are given below. So anyway, that's not the point. The main point I want to make is that there is a national mission, quantum technology document. It already exists and has addressed many of the issues which are discussed here. This basic framework is still okay. Strategic corrections may be needed, but starting ab initio is not advisable. I want to make some real live comments. These are some of the patents, recent patents from one company, IonQ. And you see the patents, you look at the list of patents. These are not all about qubit development. They are about various things that go into it. And it is quite likely that many of them will make money in things, applications other than the intended ones. But another reality check. These are the share prices of the two companies I like.
Excuse me, are you showing some presentation?
I thought was doing very well.
Are you showing any
share prices have fallen 61% in the last year. Rigetti share price has fallen 92% last year.
Kailash sir?
So we need to be realistic about the economic outcomes.
Sir, are you showing any presentation?
To understand what is working and what is not working quite dispassionately.
Sir, if you are showing a presentation, we are not able to see it.
I think he is not wearing his
My view
headphones.
is that it depends a lot on your
I'm calling him. I'm calling him.
If you are looking at 2 years later, you will make double the money. The chances are negligible. And this is quite the outcome which was flagged by expert opinions, flagged by Professor Okay, so my view for going forward is that we should expect outcomes after about 10 years and expect outcomes after many ups and downs. Don't choose too early. Don't make choice with limited knowledge. Need substantial push for integrated quantum photonics. Partly because I believe that many of these things will be used for other applications also. Interconnected modules may be easier for some technologies. This seems to be the one of the learning things from this symposium. Make workable type. Yes. Yeah. Okay. Oh. Yes, please.
Colonel Nath, sir.
Yeah.
Yeah, sir, we are not able to see any slides you are showing.
Oh, I'm sorry. I'm sorry. Let me go back.
Can we help him with the presentation?
We generally got the point that you are saying that already a lot of
I just go to the last
deliberation has gone on and some documents are available with us as far as the roadmap is concerned. So we should generally look at that and not start ab
It will
initio.
get modified.
Yes, and
It will get modified.
yes.
There's no, and it has. What I have pointed out is
Yeah.
that some areas progress has been faster, some areas has been slower. We have to look at that. Okay.
And not be too impatient in results. But I want
Absolutely.
to ask you one thing, that how do you keep the government interest alive as far as the funding is concerned? Because unless and until they see some intermediate results, suddenly the funding, the pattern tends to die down and peter away and all those things. So that is
I
not
would say the government listens to well-reasoned things. We need to reason it. We need to reason it dispassionately, not because I am pushing it, I must get it through. They have questions to ask, which are reasonable questions, and we should be willing to answer them.
Thank you, sir. Thank you. Can we have Professor Vijayaraghavan?
Yeah, hi. So I do agree with some of the things Professor Kailash said, and maybe to address your point, Colonel, I think we will have to strategize by carefully choosing things which can get to an advanced stage very quickly, while doing the more challenging long-term things in parallel. So this will require some planning where we choose these goals carefully, so that you have things to show. While the things which will take time, that will keep happening, and that way you can keep the interest alive as well. I mean, it's not just the government, even though in our case we are talking about our primary source of funds. But I think on the whole, people will get impatient if things don't produce results. But we have to remember something which is very important, and I think it's connected with what Professor Kailash is saying. One very different thing about our big mission is that, unlike other countries who had 30 years of prior work and funds building up on which they have launched their big programs, we have maybe at most 5 years. And even though we cannot compare that exactly, because we are we have read those papers and we have been in touch with those developments, so we don't need those 30 years at the same period, but it makes a huge difference. So as it's clear from the DST's program, and this is something we had pointed out at the time when DST's Quest program was being planned, that it takes a lot of time to get the infrastructure going. We have procedures which are slower. It's a lot complicated for us to import things, to set up big labs, and but I think some of the groundwork, thanks to Quest, has already happened. So when we now start taking projects, we don't have to wait for the infrastructure to come for everything. There is still a lot of infrastructure to be set up. So we have to find ways to accelerate that, so that we are not just spending half of the mission's time just building labs and waiting for equipment to arrive. And unfortunately, you cannot do anything without those pieces of equipment. So that's going to be something we have to do strategically. Coming to the list of questions you have sent, I mean, identifying institutes and all is fine. Now, when you come to quantum computing, again, the players are small, so it's fairly obvious who has the expertise where. The trick really is to bring everybody together to work on some common goals, and how to at the same time distribute the tasks. It's not going to be feasible to imagine that everybody will leave their posts and come to one location and work for the next 5 years. I mean, this is almost impossible. So one has to find a way to create a plan which distributes the tasks, and then ultimately, let's say that in one of the areas the goal is to build some n-qubit quantum computer. That can come up, the final machine can come up in one location. But all the different components which go into it, the various testings, the various R&D could happen in a distributed fashion. So this has to be thought out carefully, in a smaller group of people and have discussions. It's not something we can decide in a forum like this. That's what I wanted to say.
Thank you, Professor Vijayaraghavan. I think you have brought out very, very pertinent points, and we will take note of these, and we will also expect your detailed comments, so that, as I told you earlier when we started, that we will be coming out with a white paper which we will be submitting to the government based on your comments and the outcomes of this symposium. So everyone's views, everyone's ideas are very valuable for us. We will be putting it across to the government in the way you are saying. Thank you. So can we have our next panelist online? Anyone who's left online?
Sir, Professor Anirban Pathak may want.
Professor Anirban Pathak.
I plan to speak in the next session, but if most of my views are in sync with what Professor Ustaki has told and what Vijay has just told. This require patience means and we are probably running a bit slow means than what is expected. So things to need to take a pace means the mission which is announced has to really start. But the previous mission has really enhanced the community means earlier we were very few people who can discuss quantum cryptography. Now there are so many people, so many groups, so many activities in Pune, Hyderabad. So things are encouraging in some sense, but at the same time, when we look at the speed means we're waiting for NMQTA to be launched for a while but I keep my comment short and I'll speak more in the next session means when
Thank you.
it's properly
And I just want to throw a cue to you all. Can any sort of collaboration, maybe with some foreign partners, accelerate our journey towards the end goal? Anyone can respond to that?
So, I believe it can help, but leave it to the people who are actually tasked with the job.
Yes.
It's often in the individual level and in some of the initiative has actually damaged the possibility. So, for example, there was a program which was announced very big and a collaboration between Indian scientists living abroad with NRI and POI and Indian scientists working here. And Summit collected all the proposals and then there is no window who can respond what happened to those proposals. Then we made several meetings conducted by embassy and there were much discussion, but it never led to a contact point where people can know what happened to those ideas. And this means without a plan, discussing these ideas of international collaborations not leading to anything is actually damaging the collaboration possibility.
Okay, thank you. Yeah, Dr. Kasturi Saha. Yeah, can you increase your volume? Not able to hear you.
Hello, can you hear me?
Yeah.
Yeah, so I mean, I will echo almost everybody's points here that, while we are doing things, we are sort of running behind in time because of many of the hindrances that we are facing at several levels. And it would be better that, if we sort of clean up our pathways a little bit and try to proceed towards an integrated goal. I think that would be and that will also bring us automatically together, I think, because we are all motivated people, we want to do something for the country. And I think there are some glitches there, here and there, and we've been announcing many things, but to follow up and do something is what we need to really speed up on.
Yeah.
Thank you.
Yeah. Thank you.
So Professor
Dr.
Arvind is there, sir.
Dr. Arvind wanted to say something.
Yeah, good. So I think I just want to add a few points. Many points have been made by Professor Stogi and Vijay Raghavan and so on. See, first thing is to be realistic. This whole idea that very quickly we'll have a quantum computer, it's not going to happen that way. The reasons are very clear that, as Vijay Raghavan mentioned, that we don't have 30 years of work behind it. That's one, of course. I mean, we are starting very late. We should have started on all this in year 2000 or maybe 99. So I'm not saying that we should not do it now, but we should know what are our weaknesses. One weakness is starting very late. The second point we should be very sensitive to is that this whole idea of industry, academia, collaboration, we don't have a culture for it. So this culture also needs to be built where academia and industry can collaborate. And how to build it, we should brainstorm on that. It is not going to happen just by inviting industry and academia on the same forum and organizing conferences. One needs to put together motives for such a development. That is the second point I want to make. And the third point is that we should also think about thinking out of the box, in the sense that at the moment we are just following the threads which people have started over the years. Of course we should follow them, but part of our effort should be to look for completely new ideas, completely new solutions, completely new technologies. So these are the 3 points I would like to add to the discussion on this forum. Thank you.
Thank you, sir. Thank you. So we move on to the people sitting here. We can go from one side. Yeah.
Good afternoon, all. First
Sorry,
thing is
you can please tell your name also.
Yes, first time. I am Venkat Ramaraju Chelle, Director, Quantum Technology, Telecom Engineering Center, Department of Telecom. We are working towards the standardization of the products in quantum technology and all IT, especially telecom and related IT, ICT products also. We are doing still, now we are exclusively doing for quantum technology. We already released the quantum key distribution product already released, standardization. Now it is a final stage for the test procedure also for the product. And we got QNU lab also as requested for testing also. This is our vision, is to bring the products under standards as and when it get matured. That is our target. Next thing is that in this process we are ready to come forward to do as and when it get ready. That is the one process and make a facilitation for industry. The second part is that recently it has been decided that IPR has to be coordinated to create a IPRs, and because in the field many people are not finding much in guidance on how to make it IPRs and focus and get generation IPR generation. Especially from top also they are very concerned about the IPR creation. We may come up some follow-up on IPR. Certainly we want to do across the industry, academia, research institutes, all PSUs and all who may be contribution in the technology. The third point is that as everybody knows, everybody will work on ISO solo mode, which is most undesired for the country interest. Now everybody is realizing that the importance of the collaboration. So that's this symposium at least to come forward. You task action plans, segregate these technology and subsystem wise, and who are the partners fit based on the identification here. Further consultation in the academia as well as research institutes, industry and other subject to experts. We should come forward to make a concrete plan of action. The government is very keen to support on this part, and even recent Telecom Technology Development Fund also, they come forward to support the who is indirectly contribution towards the public utility. So quantum also, we have recommended quantum also, one of the sector it is equally important because security is prospectus. Especially the security is concerned, is very government is taking very serious, and this is the time to identify the labs where it is to be established, because this is accelerate the, and GIL has to, we have to further accelerate the GIL in the innovators, the academy and others. So please come forward the lab establishment also. We also will contribute how to make accelerate it. That's further we will speak.
Yeah, thank you.
Please.
Thank you. I think let us get some very actionable inputs which we can translate on ground.
I'll be very, very crisp.
Yes.
So myself, Pradeep. So I'm co-founder and CEO of Qubit Labs. So just to share my background is an IIT IM graduate. And just to share a few listings, I think we all are concluding that we should have a single, the centralized approach to tackle the quantum developments. But we have to understand one thing, that to have this, we all need to have a single, the team should be motivated enough. And right now the kind of structure what we are having, that people are working in a fragmented approach, and to have the motivation, the right set of motivation, it's very important to define the right roles and responsibilities of all these organizations. And I am very thankful to C-DAC to bringing out this symposium, to at least making the first step towards it.
So in my opinion, I think C-DAC could be the best body to drive the quantum developments. And if we have a clear motivations, if we have a right set of roles and responsibilities, I think the ambiguity will be less. It will be no insecurity in terms of the bodies or the departments who are working. This is the major challenge we have been facing for the last 2-3 decades. And I think that is it. Just to add on what we are doing as a Qubit Labs, we are working on PQC and then error correcting codes. And then since our core expertise is on FPGAs, and we are trying to work on some simulations and which can be utilized in a longer run in quantum developments. And I think before I conclude, I think we need to understand why do we need this quantum computer. I mean, if we can answer this question, I think the right set of motivation will be there for all the people. We all will be moving towards a single goal, and at least we will be, our efforts and it will be measurable towards the success. Thank you.
Thank you. Yeah, Dr. Sardar.
Hello. Hello. Yeah, good afternoon all. I am Dr. Santu Sardar, Director of DRDO Young Scientist Lab, working on quantum technologies. So first of all, I thank C-DAC for inviting me in this symposium, and it's been a very important learning experience for me. There have been lots of inputs we have received from the experts. So one point that we have all agreeing on is that we need to synergize our efforts to move faster and quickly towards the further developments. So in that, I would like to make a few more comments or few more inputs to the audience. What are the efforts that has been done in DRDO till date? So there are good amount of options available to encourage both academia and industry. So we know that there are center of excellences that has been established both in IIT Delhi and IISc, and there one of the vertical is quantum technologies. And these center of excellences promotes both funding towards academia as well as industry. So they are called DRDO Industry Academia Center of Excellence. Other than that, to promote our industry, there are efforts on transfer of technologies. Then we have our technology development fund. We have our development come production partners. So all these guidelines, everything is available on the internet. So people can go towards the DRDO website and check. And in academia, we have our research collaboration services as well as grant-in-aid fundings for very low TRL level activities. And in specific to quantum computing activity, what is happening in our lab in collaboration with our Vijay Raghavan sir from TIFR. So there also we have collaborations both from academia as well as industry. So we have Vijay sir from TIFR Mumbai, ourselves, and as well as TCS is contributing their part. So in project level also there are collaborations, and each of us are contributing what we can do best towards this activity. So this is one of the input to the audience here. And along with that, I have our Sahu sir, who is also from DRDO. He wants to add.
Yeah, thank you, Santu. Good afternoon, everyone, and thank you for inviting me for this symposium. Myself, Dr. Harish Sahu, scientist in DRDO Delhi. And the points are nicely covered by my colleague, Dr. Santu, already. So I would like to add some points to his points already covered. And in that, I would like to, in my opinion, we should have an assembled quantum computer quickly by outsourcing or getting components from outside, like startup like Quantware or other European startups. So what approach they have followed? In 3 years or some few years, they are able to produce quantum processors. So what we can do is, with the price they have mentioned, there is the $300,000 QPU they can provide, 25 qubits. So what we can do as, whatever activity we are doing, that's good, but parallelly we can have a quantum computer of reasonable qubits at our country. And on that, different academic institutes and industries can come up and can contribute in developing the subcomponents with their expertise. So whenever these subcomponents or the other things are developed, they can be plugged into that system and we can move towards a total indigenous system in future. And since our country has strength in software, so we should focus on that also. Don't wait for the quantum computer to come. So for that, this C-DAC has already provided this quantum simulator, and there are other quantum simulators and quantum processors available online. So what we can do is, wherever our strength is there in software development for this stack of quantum computing, so we can have codes for this quantum error corrections, circuit optimization, because we need to create a circuit and then need to optimize. So what we can do is, these activities we can do in parallel, and these are our expertise, so these can be done in parallel. And once we have the indigenous quantum computers with us, then we can plug those things in the system.
Thank you. Yeah.
Hello, good afternoon, everyone. I'm Gautam Pal from Indian Statistical Institute. So most of the relevant points have already been covered, so I would not like to repeat them, but I want to add one point which may be a little off the track. So of course there are many nice project proposals that are being discussed and coming up, and which is needed in India. But most of them are what I would say that too much well-defined to have some scope for new innovations, right? So for example, when we write projects, it is expected that we'll write what will be the end deliverables, what we will deliver after 6 months, after 12 months, after 18 months, after 24 months, and so on. So that means we know the solution, how we will solve it, what will be the solution approach, those also we have to write in the project proposal. So most of the cases it is assumed that the solution is already there, some kind of semi-product will be developed, and maybe with industry collaboration, a complete productization can be done. So that will translate only what is known to us. But if we want to innovate something new, then there have to be scope of failure, scope of experimentation, right? So along with target-oriented, mission-oriented projects, there also should be open domain projects, which will, I think, help in new innovations. Okay? So that's one input.
Hello, everyone. I am Dr. Prabhakar Krishnan. I come from Amrita University. Amrita University has established some research and product developments over the period of years in security and classical cryptography. And personally, I've been involved in the HPC ecosystem. Over the period of 2 years, 2 days rather, we had an excellent introduction of quantum and all that. So let me build up the context for my views. A couple of points I want to throw out to build, from the academic point of view. So we have seen the evolution of computing architectures, monolithic to SIMD processors and microprocessors and GPUs. So everything has disrupted. Every time we had some disruption in terms of virtualization, hypervisors, and then software architectures are very important. Somebody pointed out software is important, like Hadoop and Spark, and so all we are trying to, there is a need of, rapidly growing now to process the data. So that's the reason why I think we are looking at quantum. And so traditionally we call a computer which some processor, memory, and I/O. So now we are looking at GPU, just processor. What about memory? What about I/O? What are the other, components? So I think this question we have to ask, is this quantum computer system ready? So when, historically, look, one decade back when the GPU hit the markets, that we had, we had some struggle, learning curve, how to, process the data, how to, line up the instruction set and all that. But still it was, it blended into our classical architecture. We were, pretty much, we didn't have, much inertia in adapting the quantum. So now we are looking at quantum computers, quantum networks, built on the phenomena of physics, which is entanglement, superposition, all that, which most of things we don't understand as a computer scientist. Rather, I am be honest with that. So with all this thing right there, computers are all about very clear logic, right? 0 or 1, binary 0 or 1, that's it. So anything in between that we don't know. We call this as error or bug and throw the packet out, throw the instructions out. So, and when you get into the quantum computing, communications, networking is a classical phenomena. It's putting together all the communications and endpoints and all that together creates a network. So then we talk about security. So there is a case there recently, many, I think fellow panel members like Sunil Gupta and Qubit, some few people are there in the Indian market addressing the security part of it. So security is, has to be proven to be a business case, that it is secure. So now only quantum computer is the main driver for quantum networking and quantum security. We are making a case that all the RSAs and all the algorithms can be broken. Source algorithm factorization can be done in a millisecond using computers. So all the existing asymmetric cryptography is out of the table. So do we have a quantum computer to break that, to make a business case? So I think that's the reason I think we are not seeing any interest from the industries to say that, hey, okay, we need a quantum security product today. But though we are looking at post-quantum cryptographies and all that, just like fellow DRDO member said, we have to build all other stuff while when the quantum computer is ready, then we have to face the threat. And having said the context, I just want to put my thoughts on the questions that what we are deliberating. And point number one is we have to assemble a critical mass and niche area. The problem is carrier options are unclear. So very often all this new technology, when it disrupts, enters, we have to have a critical mass. We have core developers. Back then in 20, 30 years ago, when India stepped into the supercomputing HPC, we had core developers who were motivated, who thought that this is a good carrier option that we all assemble, which I am one among them, privileged ones. So we thought that it's a real carrier path, and we assembled, and then critical mass was assembled here in Pune. Then we were able to build a Param supercomputer, and rest is the history. So I think we have to develop that culture of how to create a critical mass here, and onboard some active working groups to work on other components and subsystems. And second thing is quantum technologies have to be engineered these days. Everything, it has to be packaged. So it cannot be so abstract, So we have to find a way to engineer a system, be it a computer, be it a communication. So we have to bring these systems into the labs, of all the, for scholarship, for research scholarship. So and then build an academic curriculum around it. So what you cannot explain, we cannot build on it. That's something that, Feynman told. What I build is what I can understand, right? So we really have to, ask some fellow member told about why do we need quantum computer? That question is a very, very deep question. I don't know many people have that answers, believe me. And we have to also build some reliable bridge or converters, adapters, for example, from the binary bit to the qubit. For example, if I'm doing a programming quantum ML, how to do a cluster, simple, SVM algorithm, how to, convert the data sets, which is binary into qubit. So it could be as simple as that. These are some of the gaps I'm finding in academia. That's why I'm pointing it out. And for the mainstream, just like how LRZ, Laura said, we have to build experimental platform and pods for agile development. So we have to fail fast. So I think we don't want to wait for the holy grail, everything is cool, like, we are looking at 9% to 25% of QBER in the communication, the thing I'm working right now, which is like 25% of the data, when you transmit a, 1K, 2K, 1024-bit key, it is 25% error is thrown in and, it's gone. So we don't need a hacker to hack it, They say a triad, confidentiality, integrity, and availability. Integrity is lost. So whatever you're looking at, whatever you're trying to solve, right? So 75% of the data or 25% of the data is corrupted because of the limitations in the physics or whatever it is. Then as a computer engineer, as a communication engineer, I have to do a lot of compensation, reconciliation, all that stuff we are doing right now with the existing quantum communication theories now. So I think that one, and then finally, just one more point I want to add. It's kind of, we can look at how Indian telecom revolution happened over the past decade. We were one of the fastest in the planet, adopted the 3G and 4G. And now with 6G and beyond with AI, everything, all the processing, AI happens at the edge. So we have to think about how to turn that limitations of quantum. For example, quantum computer processor have a lot of errors and all that. So we build, why do we have to scale up? We can build some small HPC containers, like 2-qubit or 4-qubit machines. And then quantum communication, there's an error. So don't transmit the data. Why do you have to move the data from the edge to the cloud? So localize the data. So what I'm trying to tell you is, like, we could turn that limitations into our advantage. Deploy at the edge all the HPC containers or pods, make the edge very fluid, because anyway all this data, we are building this so-called computer to process data, big data, right? So in future it's going to be mandated also to manage the privacy part of it. So not customers who are data we are mining, observing, monitoring, they don't want the data to be processed to the cloud, any big guys, right? So, and then that is one thing. I think the idea is to create new markets. So markets, just like my fellow member told, we have to build products, right? So we can say that we can define a product, something for the edge. So as a closing statement, I'd say if you look at the investments across the globe, only government and state-sponsored projects are there. So we pray India to continue to invest, just like how we had invested in the Quest program 4 or 5 years ago. We pray India continues to invest into research and research scholarship avenues to take India on parity. I think not really, dominate or something. We can say that we can be on parity and then participate in the same, realm of, computation.
Thank you. Thank you. Can we have the next panelist, please?
Good afternoon. I am Dr. Nishit Kumar Das from Variable Energy Cyclotron Center under Department of Atomic Energy, Kolkata. This is a great challenging project indeed, and I think there is generous funding from government also in all research projects so far. So I would be happy to be associated with this project. I mean, my team, my institute. We have had a first round talk with our director. And our capability is we can develop a prototype system in our center, dilution refrigerator part. And of course, as the other members said, there will be weaknesses, limitations, shortcomings that will be faced off, and let's see how we can progress. That's all from my side. Thank you very much.
Thank you.
Hello. Good afternoon to everyone. I'm very much thank you for letting me to invite this as a panelist. And this conference, it's a very new thing to me. I've learned many things which I didn't know. But however, what I can see from the conference that we could help for this development of this project. We could be helpful to develop the cryogenic system, which is basically the platform where where other systems works. So so we have some experience, and we really very much interested to take the challenge. However, the system is very complex, but it is possible, and we can go ahead with the system, because indigenously developed in a long run, it will help for the project. And as my colleagues has already told, we can go for initially R&D with prototype, and I'd like to mention that one thing also, that we should go for the dry system using the PT cooler, because that will avoid the complexities of liquid helium, handling of liquid helium and all. And this is the new things. We should go for this, and that's all. And it is a better, we can have collaboration with some laboratories so that we can go even faster. Thank you.
I just add to one point. We have already developed the dilution refrigerator and we have demonstrated it up to 50 millikelvin. That is a weight system. We used liquid helium externally. So supply liquid helium is not always very smooth and seamless. So we need, for continuous operation, we need a separate helium installation which involves power and manpower. That is not desirable for a primary project like this. So internationally, the dry systems are used. And dry system have a stable thermal distribution inside the internal thermal and residual load as well. So that can be handled once for all. Thank you very much.
Thank you. Anyone left online to express his opinion? Online, just can you go online again?
Yeah, sorry, I actually just had a question for the person who just spoke. When you said you have demonstrated a dilution refrigerator, have you built the dilution unit as well? Or?
Yes, sir. Yes, sir. We have built it and our publications are available in Cryogenics Journal, the best journal on cryogenics. And references are there in our presentation also. And including the complete in current science after this run data already presented, including the graphs.
Okay, thank you.
Thank you very much, sir.
I think that brings us to the end of this valedictory session. Contrary to my expectations, I think we have been a very well-behaved panel. I expected a lot of heated discussions, arguments, but nothing of that sort happened. But a lot of my questions which I have posed to you remain unanswered. So I request you to, take it offline and send the replies, as many of replies you can by email. We'll be, incorporating them because I want those things coming out crisply. Yes, Professor Agwan.
Yeah, so I thought I'll just add something, in connection to what has been planned in the mission. There were some questions about having projects of different types. All of that is actually within the scope of the overall, structure that is proposed. It will be the responsibility of the hub, which leads the effort to decide which areas to focus on. Which projects are, advanced projects where we want to build a complete system, which are exploratory projects, whom to invite, whether by nomination or by open calls. So this is all, there in the structure, and basically the hub's leadership will have to make these kind of calls. There is also, some confusion and maybe lack of clarity on exactly how the hub is supposed to function. We have at least examples from the ongoing, interdisciplinary cyber-physical, the NMI CPS mission, which has been going on for a few years now, and where one of the hubs actually is in IISER Pune on quantum technologies. But there is still, a lot of confusion on exactly what the mode of operation is, who's responsible and how these projects will be actually executed. And we hope to get clarity on that from DST and others involved in this. And I myself am hoping for some clarity, because this will give us a better idea on how to go about planning this. So I just wanted to add that I don't think we will have to completely avoid exploratory projects. In fact, we should not do that, and there will be scope for that.
Sir, let me clarify that. This is nothing to do about the hub. Why we wanted to build this white paper was to give more feedback to the government, because I've, after the first few sessions only, I felt that this symposium is having a lot of integrated participation, a lot of people from all over, and a lot of valuable inputs. So those inputs should not be lost, and they probably can be used to give a fair idea as to how, in case we can put our minds together, the roadmap could be shaped, and in case any previous thinking has gone in, probably it might need to undergo certain modifications in light of what has happened in the last 2 days. So that is the whole aim. Nothing to do about responsibilities of the hub or anything. So the aim of creating the white paper was just that. And we would be doing that, and we would still like your opinions. And please don't restrict yourselves to the questions. This is just indicators. In case there are certain other opinions, we would really like a lot of opinions from you so that we can have a good concept paper or a white paper prepared for everybody's benefit. With that, I thank you all for participating in this valedictory session, and look forward to your further be in touch, further collaboration and further interactions. Thank you so much.
Thank you everyone. Now I request Colonel Lekinath to felicitate the panelists. Thank you everyone. नहीं सर, वो एडजस्ट कर रहे हैं. Now we'll continue with the next session, which is on quantum algorithm and quantum error correction. The session is chaired by Dr. Rajendra Joshi, Senior Director and HOD, HPC MNBA Group, C-DAC Pune. Let us proceed to the panel discussion. With the permission of session chair, I would like to call Dr. Natarajan Venkatachalam, SETS Chennai, Professor Prasanta Panigrahi, IISER Kolkata, Dr. Gautam Paul, ISI Kolkata, Dr. L. Venkata Subramaniam, IBM, and the online panelists are Professor Anirban Pathak, HOD, JIIT Noida, Professor Bhanu Pratap Das, TCG Crest, Kolkata, Professor Apurva Patel, IISc Bangalore, Professor Amlan Chakravarti, University of Calcutta, Kolkata. I request please the offline panelists to be on dais. Now I request our session chair to proceed with the panel discussion.
Welcome to the panel discussion. I think this is specifically on quantum algorithms and quantum error correction. Myself, I am Dr. Rajendra Joshi. I am heading the HPC Medical and Bioinformatics Applications Group. I generally represent the applications development community because we use a lot of high-performance computing machines, and we have developed a lot of codes which use parallel computing and other technologies. Just to give you a couple of sentences on that, I think the application domain, specifically in the science and engineering, there's a huge need of computing. I think the need is so much that probably the classical computers, both parallel computers as well as accelerators like GPUs and others, are unable to kind of match the pace of what kind of performance is required. And all verticals, whether it's life sciences, whether it's weather forecasting, whether it's seismic data processing or computational fluid dynamics, astronomy, I think these are all verticals which require enormous amount of computing power. And very clearly, even the current machines, you'll see that they are falling short of what is expected. So the applications development communities has a lot of expectations from the quantum computing community that hopefully they will be able to solve the problems, because as all of you know, I think HPC machines have their own problems in terms of huge amount of power requirement. It has problems of cooling. I think these are all very classic cases where the kind of bottlenecks that are existing in the high performance computing, and the hope is that one day the quantum computing, when it comes up, I think it will solve many of these issues, and make it more, we move more towards green computing, so that's the kind of expectations that the HPC applications development community has. So I would like to welcome this panel. I think we have a very esteemed panel. We have Professor Apurva Patel from IISc Bangalore, Professor Prasanna Panigrahi from IISER Kolkata, Anirban Chakrabarti from University of Calcutta, Anirban Pathak, who is from JIIT Noida, Dr. Bhanu Pratap Das from TCG Crest Kolkata, Dr. Natarajan Venkatachalam, SETS Chennai, Dr. Gautam Paul, ISI Calcutta, and Dr. L. Venkat Subramaniam, IBM. So we have about 1 hour 20 minutes here. That's what has been listed, and roughly about 5 to 7 minutes per speaker. So I'll request all speakers to please stick to the timeline so that we are able to manage the schedule in a proper way. So may I request Professor Apurva Patel, who is online, to start off with his comments.
Okay, can you hear me?
Yes, sir.
Fine. Thank you very much for inviting me to give my opinion in this particular session. I will start from the basics. Let us remember why was quantum mechanics invented? It was invented because physical phenomena were observed that could not be explained by the existing laws, those laws of classical physics which were known at that particular time. And this was not a question of the classical derivation becoming too complicated or it becoming too long so that it could not be kept track of. It was just that classical uh, understanding was not capable of explaining the physically observed phenomena, and new algebra and mathematics had to be put in place. So that tells us something very important, that where will quantum technology be useful? It will be useful where the underlying signals and phenomena that you want to study are of quantum nature. This is an important point. There are lots of phenomena which are classically well understood. The classical laws suffice to give a very good description of those phenomena, and we can tackle them using classical devices. Those phenomena are not going to give you a quantum advantage in terms of new logic and new devices, and that is very practical point. We have our laptop and mobile phones which are using every day. Our classical systems have designed them and they are very practical, and we are not going to throw away and replace them by quantum devices because there is nothing that they do where the quantum signals are important. The quantum signals will be important in spatial systems, and that means that the devices which will be exploiting them to give an advantage will be special purpose devices. They are not going to be general purpose systems because there are lots of classical problems, and for that we don't need special purpose quantum devices, and even if you make them, they are not going to give us a huge advantage. So we should focus on this kind of problems. That is a very important point to understand, that they are all not general purpose, but special purpose devices, and the signals and the problems which are going to be useful to give us an advantage will be quantum signals. All the phenomena will have quantum underlying features. So now one can ask, which particular phenomena have these underlying quantum features where the classical physics does not do a good job in explaining? So one of those things is in applications with sensors and high precision measurement. What we learned is that quantum signals in various systems have both features of particle and wave dynamics simultaneously. This is a loose description, but it is good enough. And if we want to use those particle and wave features simultaneously, quantum devices will be useful. They can be good sensors. All we need to now understand is these features, which can be phrased in different ways. Say you can call it intensity and phase. They are important variables. Both have certain kind of information. The quantum signals will have both of them. And if we can bring them up to a macroscopic level to make use in a dedicated device, that will give us new information. Of course, that will require that we have a good classical peripheral system which connects to these underlying quantum signals and maintains the quantum features in particular manner. And this is a sophisticated structure we have to build, but they are all going to be hybrid systems. A small quantum part which senses the signal and a large classical peripheral system which will bring it up to the macroscopic level where we can observe. So this is one particular topic which can exploit the quantum nature of the physical phenomena, and the applications are all over the place. You can measure every physical property by this technique. Maybe it is time, maybe it is space, maybe it is motion, maybe it is rotation, maybe it is electric field, whether it's a magnetic field, maybe it's a gravitational field, maybe it is imaging. You can think of everything which we measure. They all can be improved if you can extract the underlying quantum feature by a technique which connects the quantum signal to our macroscopic level of observation. The other feature or other field which falls into the same category are understanding of phenomena at the quantum level which have intrinsically quantum dynamics. And these kind of phenomena are well known in physics or chemistry. There are lots of examples where such things are necessary, and we must look for systems where this quantum underlying signal plays an important role in the dynamics. If you can find such systems, and again I can say that there are lots of models in physics and chemistry where classical explanation is good enough, and there we do not get too much more by putting everything on a quantum level. We have to look for quantum phenomena which play an important role in the dynamics. And now if you want to understand this phenomena or model them in some particular manner or make some predictions of their behavior, then we have to have quantum degrees of freedom which can mimic whatever is going on in the real world, which is the true aim, versus a model which is an approximation of that real world into a system which we can control. This is the subject of simulations. And there are simulations of physics models, quantum chemistry, and even some candidates in biology where quantum phenomena are expected to play an important role. And if we can put them and model them properly in a physics system, in a real model, which is a computer, then you will learn something new or even learn how to design new particular things. But we again must focus on phenomena where the dynamics which we are trying to understand is quantum, and that is not a general purpose machine. It is again a special purpose study of various devices, and we must look for such problems. There is a lot of hype in the media and even expert opinions and industry projections which miss this important point, that we are trying to look for specific devices which the quantum dynamics is the underlying rule. And if you make all kind of projections without keeping this fact in mind, you do a great disservice to this particular field. And the latest example I will quote even before anybody asks me is the Time magazine. The latest cover story is, sorry to say, but it's a hype. And that kind of a description without understanding the basics of the scientific content is not going to get us anywhere. So the bottom line is again this, that look for phenomena where quantum dynamics is important and try to model those things into our systems, then we'll get real quantum advantage. All the other stuff, the classical devices are just going to do fine. And I can give examples, but that I can say a little bit later if somebody asks me. Thank you.
Thank you, sir. I think wonderful that you are able to paint a real, the real picture behind the entire quantum computing revolution that's happening. And also, you know, your remarks have been really well taken. We'll move to the next speaker. Probably we'll if we have time, we'll have a discussion at the end of the panel. So the next speaker is Professor Prasanta Panigrahi.
Okay, so I will, keeping in mind that this is about algorithm and error correction. So first I'll make some general comments about that, then go about a bit more specifically about the kind of project C-DAC is aiming at. and then the manpower part where they will come from, and then finally, little bit about, this thing which needs to be emphasized, general questions which were asked, that what kind of technology should be emphasized, maybe a little bit biased opinion of mine, I'll give about that. So, I mean, pretty much keeping with Apurva that we should cut out the hype in this kind of thing. So I'll tell you about my own story, and we started in PRL where we started the division with Professor Girish Agarwal of quantum optics and quantum information. All of us were trained individuals in quantum mechanics, have taught quantum mechanics 1, 2, 3, advanced everything, but when the division started, none of us knew which problem to attack. So there was this young boy, Monu Gupta, who came from Anirban Pathak, and together, our entire division, we were wondering about what to do. So then first thing that occurred, everybody talks about entangled states, which we knew, like singlet and triplet, but never really appreciated the meaning of entanglement. And then, suppose the entanglement is gone, maybe because somebody has solved it, maybe because of the coherence, how do you know that the quantum computer is really working? And then first of all, you have to certify that it's a good problem. Indeed, it was a good problem. Then Manu, myself, we sat down, and independently later on, I found out that Srikant and Anirban had spent similar kind of, hours thinking about it. That how do you extract? Suppose you take a Bell state. How do you extract? How do you know that it's a Bell state? And then how do you check that it is part of the quantum computer and it has not deteriorated? That means you have to find out that it is a Bell state without disturbing it. So then we design the circuit, and through Hadamard and control knot, extract the information about the parity, namely is it 0001 or 1011, and then the phase plus minus. Read it out in an ancilla and measure it on the ancilla. So the end Bell state remains intact. To our good luck, when we showed it to Professor Anil Kumar from IISc, very senior man, all the trained individuals on quantum computation in India are from his lab. He took interest, experiment was done. So you can actually do Bell state discrimination using the circuit which we had given, which he fondly called Gupta-Pani circuit. But the end result was the molecule that on which it was performed was chloroform. So chloroform seems to be the molecule having long range correlation, as Apurva pointed out. Many physical systems do manifest this kind of correlation, and one needs to sort of be careful and analyze many natural systems. But while doing it, we came to know what is called measurement. Believe it or not, that so-called measurement is very least understood. The so-called 0th chapter, collapse of the wave function, have been taught to us without much appreciation. We also found out how much of information you can extract, because we could not extract anything beyond plus minus. Then we came to know about Hall-Lebo bound. There was some great result in 70s by Hall-Lebo, and one by one you discovered in 70s, 60s, many important results were obtained about quantum information theory. Fortunately, largely due to a collective body of works from Calcutta, we sort of knew and kept abreast with that development. But quantum information, the importance of it, we came to appreciate during that work. So then suddenly you come across this so-called Bell state, and whatever we did there, we could not do it for others. Why was that? Because Bell state was maximally entangled. So then we went to characterize the entanglement, and then once you found out that it is a Bell state, if there is a mistake, how do you correct it? So through that, we came up with a error correction mechanism, which if you check, for example, in Google is close to 100 citations, and you have checked it, we have checked it in IBM circuitry. So basically error, correction, and in different kind of correlations, like for example, entanglement, discord, all those things, one should be a bit more specific task oriented. Look at the problem which you are looking at, what kind of correlations are there. For example, in communication, it may not be entanglement, it could be coherence. For example, in case of a solid state device, it could be discord. So there are finer aspects of quantum correlations, one needs to explore it in the context of the problem at hand. Now, more specifically now, coming to, for example, C-DAC, as Professor Rustagi was pointing out, there have been a body of development in the last 3-4 years, and good to know that Aninta, for example, has really kept abreast of all the trained manpower all over India. I mean, I had a couple of rounds of discussion, including one today. She has really connected the places where the individuals will get trained and who will check out the qubit and the entanglement. So I think in her hand, this project is in safe hands, and she knows the right kind of people. So you need to synergize, and that's what I think C-DAC is really doing it well. Now about manpower, where from you get trained manpower. You just check, there is a McKinsey report which claims that, and which shows with numbers, India has the largest number of trained manpower in quantum technology. You may wonder where are they. When I saw that one, I was walking around ISO Kolkata, and I found out the trained manpower exists right here. Our fourth year, fifth year students know how to handle IBM quantum computer better than us. You check how many papers from IBM are from India. Quite a large chunk of them are from IITs, IITs, and a large chunk of them from Anirban. Many of the students are well trained. Huge number of trained manpower already exists in India. You go to IBM, you go to, for example, IBM's, this person who was heading the Indian thing, Rahul Pratap Singh was my BSMS students right here. So, and if you go to Google Lab, break and build lab in California, you will see 2-3 members who passed through ISO Kolkata. And you go to Australia, for example, started Sydney Hub. 12 students from our lab went and joined last year. So the entire world is getting huge manpower from India. So they are there, and we believe them. They are our BTech MS, MTech students. Just ask them to go directly connect with IBM and get trained. They will train us. So that is there. And when it comes to technology, I would say a bit more biased towards photonics, because as Kasturi Saha pointed out in the morning, she already had a patent. Because they are the small units which can be used, and particularly for sensing. That's what I think Apurva was emphasizing. There we have a headway, and it comes to a software algorithm. We intrinsically have a headway there, because intrinsically Indians are philosophers. Hardware I cannot say, but software certainly we have a headway, and we can still do wonders there. I think I'll stop here. Thank you.
Thank you, sir. I think wonderful to hear your views, and your guidance on these points is very valuable. We'll move to the next panelist. It's Amiyan Chakrabarti, University of Calcutta.
Yeah, good afternoon to all of you. I have a presentation to share. Let me start. Yeah, so I hope that is visible to all of you, right?
Yeah.
So what I will try to quickly wrap up is basically the quantum system design, which involves the development of algorithm, then developing circuits, and obviously considering the error corrections and some new directions in this simulation and system design, okay, which are being done by my group at University of Calcutta. So we know that quantum algorithms, which are now in a very focus, is basically the optimization, and the machine learning is also coming into a great way. So we have the linear equation solver like HHL, and we have the quantum approximate optimizer algorithms are there, which are actually approximates and Hamiltonian with the variational quantum steps. And obviously, Grover's algorithms have proved very good in a lot of the logic synthesis problems involving the SAT, right? And very recently, with the IBM infrastructure, our group has solved the quantum ant problem also. So these are some of the very promising domains where quantum is showing a great promise, and a lot of business algorithms and business motivations, business use cases, business proof of concepts are coming up in this domain. And obviously, when we talk about quantum machine learning, parameterized quantum circuits and variational quantum circuits are coming, which obviously, as Professor Patel rightly said, there is a classical quantum handshake is needed in many of these algorithms in optimizing the parameters for the variational quantum circuits. So this is also an area where a lot of work can be done. Right, as we know that quantum optimization algorithms it is not true that all the algorithms can be targeted to quantum, but obviously from the algorithmic complexity, we know that the class of P is extended to BQP class in the quantum domain, and it is basically we are trying to define an Hamiltonian, which actually initiates with an initial distribution of quantum states, right, and terminates to a quantum state which is favorable for the measurement and generating the outcome. So the entire game of quantum algorithm is how to estimate the quantum Hamiltonian and how to develop the quantum functions which can approximate this quantum Hamiltonian. So the variational quantum circuits is one of this domain, and I'm not briefing it much, but this is coming into a great way how we are trying to have a classical quantum handshake. And we have seen that within a certain domain of error, this type of circuits works good, and this can be extended to a lot of algorithms like quantum neural networks, where we can actually have the weight functions which are the weight vectors which are in our neural network models can be suitably encoded in terms of parameterized quantum circuits, and we can implement the quantum neural networks in the quantum paradigm using exploiting these particular techniques. We can also exploit the convolution neural network in the quantum domain, having these quantum variational circuits and utilizing certain controlled operations, which equally trying to try to map this pooling and this subsampling domain of selecting some states out of the given number of states. It's a maximized states, and we have the quantum controlled gates which can do this operation. So a mix and match of the variational circuits and some sort of quantum reversible operations can develop this equivalent quantum neural network, the quantum convolution neural network, and these are also coming up in a great way in solving some of the complex problems in the machine learning domain. Now, if you look into the circuit and synthesis, circuit and systems domains, once we develop the algorithms, there are several techniques several steps we have to follow. Obviously, the quantum technology is the key here. Based on the quantum technology, we have to look into the quantum functions which are available in the specific quantum PMDs. And then comes for the particular specific PMD, what are the type of error correction or error encoding techniques we employ. And there are certain challenges. Obviously, the large number of qubits is still a challenge. We cannot go for a fault-tolerant quantum computing, because fault-tolerant quantum computing involves a large number of qubits for encoding, and so we are limiting ourselves at present to the NISQ era. The cost involvement and the vis-a-vis the quantum infrastructure, is obviously a sort of trade-off we have to think upon when we try to implement the real algorithms in this quantum. So most of the cases at present is that we are trying to develop a sort of proof of concept in the quantum domain of the algorithms, and we are trying to think that provided the quantum computers will come up with a larger number of qubits, right, these algorithms can have their full-blown implementations. So this is a sort of quantum CAD which was actually proposed by our group, right? And then it was published in several works that we are trying to develop a particular type of system where we have a high-level flow called QCL, and then we have a compilation. Compilation involves a lot of things. It incorporates some sort of visualizations in terms of quantum circuits, in terms of the quantum state matrices, and then we can actually get into the technology mapping, which involves how we decompose the MCT gate, how we take the basic quantum operations specific to the PMD, and obviously specific to the technology, what are my fault-tolerant libraries. Okay, so then the error correction coding, and then we can actually go to the final stage of the placement. So this is the normally whatever tools we have at presently in the quantum simulation domain follows a more or less this particular flow, and this particular flow will be much more extended when we actually look into the present scenario of error correction. So if we look into the present scenario of error correction, obviously we are in a smaller qubit size or near-term quantum computing domain, where we tell that we are in the domain of NISQ, that is the noisy intermediate scale of quantum computing, where we have less number of qubits. We are working with shallow quantum circuits, and we are trying to do repetitive measurements on the shallow quantum circuits to find out our expected results. But obviously the target is maybe in the long run, when the technology becomes much more approved, much more improved, and we can have a larger number of qubits, we can really have the encoded qubits, and we can get into the fault-tolerant quantum computing, which is obviously the future, maybe 5 years down the line. And now regarding the error correction, this is a recent work by our group where we have tried to, and this technique is done by a lot of groups. This is a publication in the ACM quantum transaction, and where we have showed that we can use machine learning in improving the quantum error reduction. So we have used a sort of technique where we have tried to generate a sort of data set for the errors for the different types of shots, for different number of shots, for different quantum circuits, where the feature space is defined in terms of the different types of quantum gates, the number of qubits, the entanglement measure, and all this type of feature space was being used. And based on the feature space, we developed a sort of regression model where we can actually try to predict the amount of error. And for a larger circuit, we see the amount of error, and we try to cut the circuit into fragments, and we try to see that whether the fragments are below a certain threshold of error, and then we try to execute the circuit, right? And that's the circuit fragmentation technique, which is now being very popular in many of the for solving the large quantum circuits and trying to execute the larger quantum circuits. The other work what we have done is basically a sort of distributed quantum compiler. This is a very recent work done by our group, and where we developed a sort of a divide and conquer based quantum compiler approach, and where we have a distributed processing among multiple computing nodes, and we can actually cut the circuit, we can simulate the smaller fractions of the circuit, and then again we can join the circuits in a proper scheduling way, and we can generate the outcome. The other interesting domain is basically the multivariate quantum computing. The multivariate quantum computing means that we can have the D-array systems in general, starts from the ternary, quaternary, and then ultimately goes to the D-array systems. And these systems, though not very much well achieved in the technology still, but there are some ion trap, some research results are there where they have implemented the ternary quantum systems or the qubit quantum systems in the ion trap domain. And we have actually developed some sort of simulation models, and we have solved some algorithms in this particular multi-valued quantum logic. We have solved some graph algorithms which shows much better results in terms of the number of computation steps or number of quantum steps compared to the binary quantum version. And we have also showed the certain synthesis techniques which involves a combination of binary and D-array systems of decomposing the multi-qubit gates, like multi-qubit Toffoli gates. It gives you a less amount of resource and less amount of quantum steps to decompose those long trees of multi-contour Toffolis. And these are some of the works we have done that instead of using the swap gates, which are basically used for decomposition or for trying to make the control and target closer to each other, multi-qubit type of intermediate gates gives you a better result. We have recently actually developed a compiler which is basically takes care into both binary. This is, I think, the first of its kind compiler. This has been developed obviously with a collaboration from Nanyang University. Professor Ruban Chattopadhyay is collaborating with us also in this particular domain, and we have developed a sort of simulator which can simulate both the binary and the ternary quantum systems in the same simulator. And this has been targeted, named as C-DAC. This is now available in an archive version. This has been submitted in a good journal, and we are hoping good results out of it. So these are also some of the techniques which are very interesting, and these are very good techniques in trying to explore the quantum machine learning and larger data space problems, and trying to put it to the quantum domain using the multi-qubit type of strategies. Last, I will try to say that we are also proposing something called quantum development life cycle. This is basically when we start discussing with the business development platforms, developing the platforms in the quantum domain of full-scale software stack. So how should we go? So this is a sort of called like a software development life cycle. We are proposing something called quantum development life cycle, which is available again as an archive paper. So this incorporates the the different stages, starting from the feasibility study, which will try to understand the quantum resource, quantum cost required, and then go into the different stages of quantum design and quantum gateway, which means that how the classical quantum handshake will be done, and then goes through the quantum testing and quantum maintenance phases, where we have the different types of analysis are required for the maintenance and augmentation of the existing quantum systems in terms of addition the quantum modules and quantum blocks in the existing quantum circuits or quantum algorithms. So I think these are the exciting areas of quantum computing, what I've highlighted, starting from the algorithm domain and some of the newer challenges and newer inroads which are available in the research domain for the past 2 to 3 years. Right, and thank you all. I will be available for the questions in the further part of this panel. Yeah.
Thank you, Professor Chakrabarty. I think it's wonderful to know about the quantum algorithms that you have been working on. Probably if time permits, we can take questions towards the end.
Sure.
I'll move to the next speaker, Professor Anirban Pathak from Noida, JIIT.
Thank you. Let me try to share my screen.
Yeah.
So is it full screen now?
Yeah, please go ahead.
I would like to thank Anita, Amit and others for inviting me, and I would prefer to be there physically, but for some personal reasons I could not be there. And initially Apurv has given a very nice introduction, and Prashant told about how we came to this, means 15 years back or something like that, means when we started. But we are more like quantum communication group or quantum cryptography group. So we are not free from decoherence, so we face error every day, but we don't work directly on error correction stabilizer code in everyday life. So, but I'll talk about some points to ponder first. The algorithm can exist and evolve in general without any kind of computer. So for example, when I was a kid and I learned how to add, so that was a systematic method for solving a problem, and that's an algorithm. When I learned how to subtract, how to multiply, those were algorithms. But some algorithms are spatial and they need specific infrastructure, hardware. The quantum algorithm is a spatial kind of algorithm, but development of algorithm is independent of quantum computers, and what we use in quantum algorithms are often hybrid. Even in Shor's algorithm, I use GCD finding algorithm, which is from Euclid, which was developed even before Christ, birth of Christ. So this thing has to be clear that it's a spatial type of algorithm which requires a specific kind of hardware. And quantum computers can show supremacy only if such algorithm exists and downperform or overperform the corresponding classical counterparts. And finally, computing will be possible even if there is a computer and there is an algorithm. Practical applications will be possible only when we can correct error. So initially we thought that it will be like analog computing and error corrections will be difficult, but when it was understood that error can be discretized and error correction is possible. So it's a complete picture that spatial type of algorithm, presence of scalable quantum computer, and error corrections will together do the purpose. Now, I would like to tell about some points which need thought. So these are not my work or anything. So there is a trust versus proof thing. So many things we do at the moment in context of quantum algorithm or classical algorithm is a trust. There is no proof. So if you believe that P is not equal to NP, you believe it. When you say that you have a confidence on hash function, that's a confidence. These are not proof. So similarly, at the moment, the strongest belief which we face as quantum cryptographers speed up solving the problems of the complexity class. My previous speaker talked about this complexity class. Problems using quantum resources in a bounded in polynomial time. But we believe that problems in NP which are outside DQP. So if I choose a problem from there and solve, make a cryptographic problem. So the assumption is that since today there is no algorithm, tomorrow there will not be any algorithm. There will be a safe cryptographic scheme called post-quantum cryptography. So post-quantum cryptography is still classical, and many of these algorithmic things are conclusions done at the moment are on trust. So a very rigorous theoretical understanding is needed that which of these can be proved and which are only trust. Now we had I started teaching a course on quantum information sometime in 2003, and showed a very interesting paper at that time. Why have not more quantum algorithms been found? So I still enjoy this, and the situation is changing, because then we thought that we live in classical world. We don't want to play and do errors and then design new algorithms. But now you have IBM quantum computing access from your phone. So nobody thought of this kind of thing in 2003. So probably the number of algorithms. But I mean, still there are only a few algorithms, and we see a large number of publications, but they can be classified into three things: Fourier transform based algorithms, growth type algorithm for simulating solving quantum physics. So this is how short classified, but now many machine learning based algorithms have appeared and things are changing quickly. But as I mentioned in the beginning, we are more like a quantum cryptography group. Right hand side is showing my cryptography setup where the tally and Bob and it's implemented. So if in my group we talk about error, normally we understand errors in generated key, error in Alice's key and Bob's key. But cryptography is not limited to secure communications only, means it's often come across secure computations, and we have interest on designing schemes. So normally we don't call them algorithm. So quantum and semi-quantum commerce, quantum and semi-quantum online voting anonymous veto, and this anonymous veto we have implemented in IBM, and we keep on doing things on IBM. We have done post-processing, we have done different kind of tomography, including process tomography. Process tomography is mean for designing that how much gate introduces on an average. And so there are those interactions with the quantum computing related things and algorithms, but we normally focus more on communications where nobody is free from decoherence. But we occasionally move to things which are in the domain of core domain of algorithms, not in the borderline area like tomography. With Anindita is physical layer and very much present in education. With Anindita, I did some work on quantum fault models. Professor Panigrahi told us about work with Manu. We started working with Manu, and then most of my algorithmics works are related to Grover's algorithm. So 15 years back with Manu, I wrote some code for some paper for distributed Grover search algorithm. And recently we have become interested in certain kind of problems like variational eigensolver. With the intern, we are trying to do something on differential equation solver. And quantum optimization algorithm is interest of couple of postdocs here, and they want to implement in my group something related to quantum finance. And we have a bit of interest in quantum machine learning, but it's again move around a particular type of Grover's algorithm. So this is a recent paper. So since it's a 5 minutes or 10 minutes talk, so it's very difficult to give even a glimpse of the activities of the group. So we just thought of putting up old paper and a new paper. So recently we have worked on we have a blurred image, and this kind of number plates are often taken by a moving car, and there is a traffic light camera and it takes a blurred image, and these are alphanumeric, and this is the easiest problem in image processing or in optical character recognition. This is easier because the font is well defined, that number plates has to be written in certain font, and it will be only alphanumeric. So we have done proposed a quantum classical hybrid algorithm where image processing is done, and the proposed algorithm can transform a low resolution bitonal image, so there is only black and white image, of a character from the set of alphanumeric characters into a high resolution image. And there is a good amount of classical part as in the source algorithm and many of the algorithms. So it's expected that full algorithm will be hybrid in some sense, and it utilizes a variant of Brovard search algorithm, which is called fixed point search algorithm. So now basic idea of our algorithm, a low resolution image of each alphanumeric character was created along with a database of high resolution image. This high resolution image had 4 times more number of pixels. One by one, each of the high resolution image was assumed to be correct one, and we compare and we create a kind of confidence value. So, and this is done using 2 kind of operations, 1 qubit operations performing 1 iterations of the fixed point algorithm, representing the individual pixels, and then a 4 qubit operation. So without going into detail, and then we implemented in C-Quasm simulators, and the results are quite encouraging, and we have calculated the complexity also. So the whole point is that there may be very fancy algorithms, but there are real-time tasks which can be done with existing technology, and just like this number plates recognition, which is a very real-time, traffic police should not go into giving a wrong challan to you because the number is recognized incorrectly, and in such situations the confidence value is increased when you use quantum algorithms. So finally, before I stop, I just want to give a message that we need to look more on the theoretical aspects of quantum algorithms too, what can be done, what cannot be done, and whether trust is restricting us from doing new things like the trust on hash functions, trust on the point that problem DQT solved. So we should even try to solve problems outside DQT. And at the same time, we'll try to look at the experimental aspects, that what is the NISQ era, what the minimum problems which you can realistically solve, like the traffic, this number plates problem. So much are to be done, and many people have windows to contribute. So not physicists, mathematicians, engineers, all can contribute in this area because this is a truly multidisciplinary area. And it also has many problems. So with this, I'll stop.
Thank you, Professor Pathak. It was wonderful to hear your work on the Grover and Shor's algorithm and how it can really be put into practice in terms of a practical application. So we'll move to the next speaker. We have Professor Bhanu Pratap Das from TCG Crest, Kolkata.
Thank you. Can you, I've shared the screen.
We are not able to see your screen. We can see you and your voice.
But we cannot see your screen.
Sorry?
Your screen is not visible as yet.
Cannot see your screen.
Oh. Actually, I had sent my talk also, just, in case there's such a problem. So I don't know if the person who had sent to can help in sharing it, maybe. All right, so is it visible now?
Not yet.
No.
Okay.
It came for a while, but it disappeared again.
Hello? Sir,
yes.
We are sharing your screen.
Sorry?
Your presentation, sorry. We are sharing your presentation.
Yeah, okay, fine. So can you all see it?
Yes.
All right, so let me begin my talk. So let me thank the organizers for inviting me to make this presentation. I had somehow assumed that the organizers are interested in specific results of quantum algorithms. So that's what I've done. So that's what I'll be doing. So I have prepared to give results for some specific quantum algorithms, but maybe towards the end, I'll also say some things that are of general interest, which some of the other speakers have done. So what I'm going to be talking about is quantum algorithms for quantum many-body systems, in particular atoms and molecules. And so I've listed my collaborators below. The first two are students. They're actually interns. Both had done the masters from ICER Kolkata. And Prasanna, my colleague, is an atomic molecular physicist, and the other two are quantum chemists. So one of the most popular algorithms, quantum algorithms for atoms and molecules is what's called the variational quantum eigensolver. And it's based on the variational principle, the Rayleigh-Ritz variational principle in quantum mechanics. And so those of you who are familiar with the variation principle know that what we need is a trial wave function, a wave function that depends on certain parameters. The wave function in variational quantum eigensolver has to be written in a very specific way. It's a unitary operator acting on a specific wave function. Now, the choice of the unitary wave function, of the unitary operator is flexible, but I think if one chooses the right unitary wave function, keeping the physics in mind, then one can get good results. And that's what I'm going to be showing today. And the unitary operator is the operator that one uses in what's called the unitary coupled cluster theory. Well, that's just a jargon. Now, you may ask, why have we chosen atoms and molecules? The reason is atoms and molecules are very suitable for quantum computing because atoms and molecules are entangled quantum many-body systems. So that means the wave function of the atoms and molecules is entangled. And in fact, the entanglement is a measure of the strength of the many-body effects. And of course, you can do these. You can calculate atomic and molecular properties on a classical computer. But if you take an atom or a molecule that's strongly entangled, then a quantum computer would potentially be better, and it offers the opportunity for quantum advantage. So far, quantum advantage has not been observed for atoms and molecules, though the field is improving steadily. And I think at some point, perhaps quantum advantage might be possible. So you see the wave function here, depends on certain parameters which have to be varied till the energy that has been chosen becomes a minimum, and that becomes the ground state energy. And then using the ground state wave function, one can calculate various ground state properties. We've also extended this to excited states. I'm not going to go into that because it's a brief presentation. So the next slide, please. Okay. Yes. Oh, sorry. Okay, I can do it myself. Okay, yeah. So the new thing that we have done is that we have extended the VQE algorithm to the relativistic regime, that's to say that we've treated the quantum many-body system, which are atoms and molecules, in the framework of Dirac theory rather than the usual Schrödinger theory. And we've done the calculations both using the non-relativistic and the relativistic frameworks, and to show that relativistic effects indeed do play a part using, we've used the VQA quantum algorithm. So we have chosen two molecules. One of them is light, beryllium hydride, and the other is heavy barium hydride. Now, it's easy to see that as an atom or a molecule becomes heavier, the nuclear charge, the charge on the nucleus increases, so the electrons experience a stronger force, so they begin to move faster. So as the system becomes heavier, the atom or the molecule becomes more and more relativistic, and that you can clearly see from the results of a VQE simulation. I should emphasize here that the results that I've shown are using VQE, but the computations have been done on a classical computer, on a Cray computer. And you can see, so and I've given the ground state energy and the dipole moment of the molecules. So if you have a diatomic molecule, there are some molecules called polar molecules where, which are made up of a positive and a negative ions. I mean, for example, beryllium hydride would be beryllium plus and hydrogen minus. So the molecule would have a dipole moment. And that's a very, very important property, both in practical applications and fundamental physics. And what I've shown here is that for something like beryllium hydride, the ground state energy, the relativistic contributions are about 1.62%, and for beryllium hydride, it's 0.02. And for the dipole moment, it's much bigger. The relativistic contribution is about 12.4%, and for beryllium hydride, it's nothing. So this was a demonstration of the importance of relativistic effects in molecules here, using the VQE algorithm, which is part classical and part quantum. Okay. Right. So now we are trying to do our computations, that is the VQE computations of ground state energies and dipole moments using actual quantum hardware. So we are considering 3 or 4 possible quantum computers which we can use. And surely we're going to have errors there, because these machines are certainly noisy. And there, I think, as the number of qubits increases, that means as the number of electrons in the atoms or the molecules increase, one would have to implement various quantum error correction schemes. And let me just say that there are 2 kinds of quantum computers. One which is based on qubits and quantum gates. So those are the more common kind of quantum computers. But there's another kind called a quantum annealer, which does not use gates, which does not use quantum gates, but only qubits. And they're really very good for optimization problems. And that is what we've tried to demonstrate here, that we have used a quantum annealer. Actually, we have used a D-Wave 5,000 qubit machine to calculate a genuine relativistic effect. That is the splitting between the energy levels. This is an atomic problem. So of boron atom, the ground state splits into 2 levels, very small, tiny splitting, which we have calculated by using an ab initio relativistic theory. So it's based on many electron Dirac theory. And now fine structure splitting is entirely relativistic, whether the ion is heavy or light. So what we've done here is that we've used what's called the quantum annealing eigensolver, which, like the variational quantum eigensolver, is also based on the variational principle. So, the idea is to write the energy in a particular way. That is, we have to expand the wave function in terms of many electron bases, which we've done. And the A alphas that you see are the coefficients. And then the energy that is to be minimized is written in terms of the coefficients A alpha. The H alpha betas are the matrix elements. And to solve it in a quantum computer, you can't do that directly. I mean, so what one has to do is to transform that. So the coefficients A's will have to be transformed in terms of qubits. So the xi, xj that you see are basically qubits. So the coefficients A can take any value from 0 to 1, I mean the absolute values. But you have to transform it in such a way that the xi's, xj's are either 0 or 1 because they're qubits. And then the expression that you see at the bottom of the slide, the last expression on the slide, is minimized. So that means the qubit, you start with an initial qubit configuration and then change that. I'll not go into the details, I don't have the time either, till you get a minimum value for the energy. So, okay, so I'm not able to go to the next slide. Oh yeah, okay, fine. Yeah, okay. Now I'm going to present the results of this fine structure splitting. Now there are two levels. We calculate both the energy levels by optimizing the qubit configuration. And as you can see, we've given results for 4 different ions. For something that's relatively light like calcium, which has 20 electrons, and then we have molybdenum, which has 42 electrons. And these results really amazed us. You know, we did these calculations both on a classical machine and on the D-Wave quantum hardware, which is the 4th column. And very unfortunately, these fine structure splittings have been measured. So that's the last column. And what we found was that the results from the quantum annealer agree with experiment on an average to about 99%. Now, you know, we've not done a full-fledged calculation on gate base, but there, the accuracy is about 40% or actually less. And even for a molecule that's as light as hydrogen, gate-based gives about 40% accuracy using VQE, for example, whereas an annealer gives 99% or better. Now, this, of course, cannot be generalized. You know, I mean, nothing can be generalized. But a system which has, 5 electrons, highly relativistic, or entirely relativistic in this case, can be handled by a quantum annealer. And this is something that has, really surprised us. And this is being now reviewed on Nature Physics. So, by and large, people, certainly in India, have neglected quantum annealers, but I think their potential must really be explored. I think this is one of the messages that I would like to send to the quantum computing community in India. One reason why I was somewhat familiar with quantum annealing because a colleague of mine at Tokyo Institute of Technology is the inventor of this. So we had a lot of discussions, but it's only when we got access to the D-Wave machine through the MATI Amazon Web project did we actually carry out these computations. Okay, so maybe that's all. I don't know if I have any more slides. Yeah, okay. So now, well, I mean, we had to sort of make some modifications to the to the quantum annealing eigensolver, which was proposed in Los Alamos, we had to change the workflow and we had to sort of introduce a new qubit encoding method. And these are all technical things. And then, the decomposition that the Los Alamos people had done was a bit random. So we made it more systematic by using quantum perturbation theory. Now, this is the first atomic calculation on a quantum annealer. It's also the first relativistic quantum calculation on a quantum annealer for any system, you see. Well, I'm an atomic molecular physicist, and I sort of work on problems that are of that are more fundamental in nature in physics. And we sort of have been looking for new physics beyond the standard model of elementary particles. And what I am working on is to extend our work on both gate-based and quantum annealing to look for new physics beyond the standard model. And this is a stepping stone. For example, the fact that we could do dipole movements, is a very promising sign, because the quantities that we'll be looking for would be similar. Now, so that is all that I have to say about our work. I mean, I've given you results for using sort of fairly popular algorithms, VQE and the quantum annealing eigensolver, the applications for atoms and molecules. But we have colleagues in our research center that work on other areas. We have a new colleague who specializes in quantum machine learning and with a computer science background. And we have collaborators with different backgrounds. I probably will continue to work on problems related to fundamental physics, but many of them will work on problems that have real-world applications. VQE is a fairly versatile algorithm. It's being, there are groups that are using it for drug design, for new materials, as well as looking for new materials for batteries of electric cars. So some of my colleagues may go in that direction, which is certainly very worthwhile. And, if you are familiar with quantum annealing, then, there are many, many possibilities of doing real-world applications. Many of you probably know that this has been, that quantum annealing has been applied in a very interesting way to address the traffic control problem. In fact, a colleague of mine in Tokyo who has a background in string theory, he's been working on it using very interesting ideas in quantum annealing. So these are problems that I think can be addressed. And another thing that I'm not directly involved in, but it's related to climate change.
Professor Das, can I interrupt you? We are running short of time. So
yes. I think I'm through. Yeah. I think let me end then. So thank you very much.
Thank you very much, sir. Thank you.
Okay.
So I'm told that there is a international speaker coming in live at 5:45. So probably one. Can we take one panelist, or we can finish it? So I'll leave it to you. If you think you can, because we just have about 10 minutes probably. I don't know. Yeah. So probably they have asked us to break and then come back, and we can do that. So thanks a lot. Thank you.
Thank you, everyone. We'll continue with this panel discussion after the keynote talk. I request Dr. David Gunnarsson, CTO, Blueforce, Helsinki, Finland, to deliver the expert talk, who is connected with us virtually.
Hello, Dr. David, you can start now.
Okay, so there was no tea break. No.
No, we will continue with your presentation.
Okay, sure. So thank you for the invitation to present Blueforce and Blueforce's role in the quantum ecosystem. My name is David Gunnarsson, and I'm the CTO at Blueforce. I also would like to thank the organizers for making this symposium. It's going to be very interesting that the quantum computing ecosystem in India and the world are coming together to discuss next steps. My talk today will be twofold. I will give a little bit background to Blueforce and our role in the quantum ecosystem, and then I will go further and discuss what kind of products we actually contribute with to sort of make the quantum technology move forward. I will jump in to the first slide here. Let's see if it changes. There we go. So who are Blueforce? So we are an engineering and manufacturing company based in Finland. We are doing cryogenic measurement systems. That's our business. And this is systems that allow the user to do measurements at temperatures that are just a few thousandths above absolute zero in temperature. The reason people need to do that in quantum technology is that if you want to harness the quantum effects for devices that operate at an energy scale that is comparable to few gigahertz to tens of gigahertz, you need to use these low temperatures to have all the noise away from the system. This is where Blueforce have been focusing from the beginning, and the core technology that we use is dilution refrigerators. 15 years ago, the company was founded by doing new dilution refrigerator technology and bringing that to the market. You have an example of a Blueforce dilution refrigerator here in the middle of the slide. So since cryogenics is an integral part of quantum technology, especially for these frequency ranges, it's become a mission from Blueforce side to actually support the quantum technology community with this type of technology that actually brings them further, both scientists and industries. And as an example, I just saw a few days ago, there was a publication in Time magazine. So on the cover of Time magazine, there was actually a picture of a Blueforce dilution refrigerator. And in this picture, you can also see that a quantum technology payload is actually sort of attached to it and then cooled down to sort of do the quantum calculation for the user. But I thought this was a good connection to sort of show that cryogenics and quantum go hand in hand, especially in this technology range. So how do we sort of accomplish our mission, and how far are we so far? So of course, Blueforce is not a small company anymore. We are 15 years this year, and we have grown from a few people to more close to 400 professionals that helps us sort of envision this mission. And we're very proud to have a very diverse workforce from more than 40 nationalities helping with this. And I think that's a testament to this technology, that it actually have sort of a promise for many that they are actually willing to even come to cold Finland and do sort of work on their passion. So as you can see, Finland at the moment is quite cold and unfriendly, but it's going to be summer soon. So, tell a little bit more about Blueforce background. We have installed more than thousands of these systems worldwide, and we have a big production capacity to actually deliver systems for the quantum computing community. And we have ambitious plans to sort of expand this production capacity, and looking forward to sort of take it to the next step during the coming years. Blueforce is also We are well established around the world, so we have sales and service representatives around the world. And I would like to especially point out that in India, we are working together with VT Vacuum Technologies. We have a long-going relationship with them, and they are specialists within cryogenics and components that you need to sort of reach cryogenic temperatures. They are based in Bangalore, and they have helped Bluefors to provide an install base in India already now for our systems. And they also can, and they do sales, and they also have sort of first-in-line support and service opportunities locally in India. We are very happy to sort of work with them, and we're looking forward to work with them when the quantum ecosystem of India is developing. So they will be a key partner for us. So with that, I sort of finished my first part, like what is the role of Bluefors in the quantum ecosystem. So as I said, our mission is to provide the cryogenic tools for the quantum computing or quantum technology community to make sure that they can take the next steps. The way we do that is that we have a scalable production facility for these cryogenic measurement systems, and we are working hard to sort of take it to the next step and make this actually an industrial supply chain for cryogenics. And the benefit of that is that you're going to get a more reliable and more predictable product base for cryogenics when quantum computing will become a more commercial application-driven commodity. With that, I go over to our product offerings. So Bluefors identify 4 different areas where we are active, especially when it comes to the quantum ecosystem. So the first one is our generic systems, which is the scientific tools that Bluefors started with. So these are sort of tools that can be used for many different purposes where you need to reach very low temperatures. They are very strongly equipped with the second box, that is the cryogenic measurement infrastructure that you have to your left. And the cryogenic measurement infrastructure, I mean how you bring signals down to these low temperatures and how you can actually extract the information from the devices that you have at these low temperatures. So this is a field where we also have developed a lot during the years, not only the cryogenics, but also to complement and add value by actually having more ready system for the user. The third one is something we call high throughput characterization. It's aimed a little bit more to the sort of creation of devices that needs to work at the low temperatures. So it's, for example, if you do device microfabrication in clean rooms, for example, you need to do characterization and understanding your processing of the devices. And the first tool we have done in this segment is something we call a cryogenic wafer prober, and that helps to sort of directly get a handle over how devices operate at cryogenic temperatures before you put them into your application. The last but not least is the large scale and industrial cryogenics. And this is Bluefors' take on how we see cryogenics evolving when there is bigger demand on cooling power and also demand on space to be able to sort of fit the technology that the user needs to reach the next levels of their roadmaps. I will talk a little bit more about our initiative in something we call KIDE in the following slides. Coming back to generic systems, as I said, this is sort of our core systems. They have been with us from the beginning. We have a few different sizes depending on how demanding experiments or application the user have. Going from a small to a larger one that we call XLD-SL system. And I think this XLD-SL system, that's the one that has become the workhorse for efforts within quantum computing, because it has the capability to have a more complex cryogenic measurement infrastructure and a bigger payload with more cooling power in the system. the current offering we have for signal paths is that you can have up to 1,000 signal paths in one of these systems. And that corresponds to operating a few hundred qubits, quantum qubits, depending on your technology. The cryogenic measurement infrastructure, as I said, it has to do with the signal path, how you take the signal from the low temperatures up to room temperature, and how you sort of control your devices at low temperatures. This is just a few examples. We have a quite vast portfolio of different ways taking signals down, but I would like to highlight the ones that we think serves sort of quantum technology at the moment. So the first one is something we call high density wiring. So it's an initiative where Bluefors try to increase the density in our current XLD SL form factor to make sure that we actually can fit 1,000 coaxial RF lines inside one of these dilution refrigerators. This is the latest Bluefors have to offer, and when it comes to components, we are filling in with components for both this high density wiring, but also for more general wiring solutions. And one addition is IR filters, which have proven to be a very useful tool to isolate the quantum devices even more. When it comes to sort of understanding your signals, etc., at these low temperatures, Bluefors standard systems, they have thermometry to understand the environment of what you're working with, but the thermometry only measures temperature, and that might not be so interesting for the user. So we developed something called a cryogenic variable temperature noise source, which helps the user to actually qualify the signal integrity of their sort of quantum devices at low temperatures. So it's a diagnostic tool to sort of get more information from low temperature of your devices. The last bit that is in this measurement infrastructure is something we just started piloting last year. It's an integrated readout module that actually allows the user, when they get the system from us, to actually have close to quantum limited signal amplification ready in the system. This is something that will be very useful because this is usually a very demanding thing to set up, but this is now sort of an integrated model that sort of works with clear specs from the beginning. Going to the third sector, which was this high throughput characterization devices. So I will deep dive on the cryogenic wafer prober a little bit, giving you a little bit more data on that. So it's a fully automatic wafer prober. And if you're familiar with microfabrication, it can handle up to the largest standard sized wafers, 300 millimeters, but also smaller wafer sizes. It has a wafer temperature well below 2 Kelvin, so you can actually probe at sort of cryogenic temperatures. There's options to also have auto loading for up to 25 wafers, so you have a cassette to cassette possibility to actually put this device into sort of a future production or serial testing of a production line. This is a unique device on the market that have this capability. And we already know that this device already increases the throughput time more than, or up to 1,000 times, but even more than 1,000 times for device test throughput, and compared to how measurements are done at the moment. This is a segment where we actually are looking into reducing the temperature to even lower temperatures to actually include other quantum technologies that actually require lower temperatures. So we are looking forward to present new advances in this in the coming years. The last bit was what I call large scale and industrial cryogenics, and here we started working on something we call a platform, a cryogenic platform, C-DAC. So C-DAC, actually, it's a Finnish for snowflake or for a crystal, and the reason for that name is that the system we came up with when we wanted to sort of make a larger system had an hexagonal footprint. So that's why you have the snowflake sort of naming. The kid or the snowflake is something that has been in the Blueforce brand from the beginning, and you see it up here in the right corner. We actually still have the kid around, so was a natural evolution of our brand into a product. KIDE was sort of the outcome of when we needed to figure out how do we do a bigger cryogenic system to sort of fulfill the needs that the community will have. And it's not that straightforward to just supersize the systems, the generic systems that we already have. Since that becomes very bulky, it's getting very hard to handle and access. So the first thing we did doing this platform KIDE was to rethink the user access. And our take on that was to create a self-supporting vacuum chamber, as you can see on the picture here, and then that it actually had multiple accesses from the side in the form of doors. This makes it easy for actually one person to still access and maintain the system, even if it's up to 5 to 6 times larger than our sort of standard systems. You still have the same usability. Another take that was necessary for the sort of new larger infrastructures of quantum technology is that you need more cooling power, and you need more sort of possibility to cool bigger areas. So the way we did that was to use multiple cooling units, and we based those cooling units on our traditional technology. So it's a well-proven technology that we now put in multiple of in this larger chamber. We didn't only put new cooling units inside, we also actually dedicated them to different tasks in the system. And this actually allowed the customer to actually have a much clearer interface to the cryogenics, where they actually can decide what temperature versus cooling power they should use. So this is actually the main reason we call this a platform instead of a system, because it actually is a device where the user actually have a clear interface that it actually can attach its technology to. Looking at the capabilities of this is a larger system, and it's actually ready to support 1,000 qubits or more. This number is just taken on looking at what technology is existing today, but with miniaturization of technology, we believe that this vessel will be able to house up to 10,000 qubits at least. The last piece is, of course, if there is need to actually expand this into a larger cluster, then you can actually have the capability of this as well. Since this system have flat interfaces, it's easier to actually do connection to other chambers and cluster multiple systems together. So we are looking forward to sort of get to see how this KIDE operates in the future, and this is sort of the final slide of my talk, and I would like to thank you all for the attention and looking forward to questions or comments from the audience. Thank you.
Yeah, David, wonderful talk you've given, and at the time when everybody was getting ready to go, and you were excited everybody again. So,
okay,
please tell us this latest KIDE you have shown.
Yes.
It can access all these 1,000 plus qubits at a time, or is there any kind of multiplexing or any scheme you have?
No, so KIDE is a very large system. So I think the diameter is close to 2 meters, and it's roughly 2.5 meters tall. So that means that with current signal technology, signal path technology, for example, our high density wiring, you can fit up to maybe 4,000 wires into this system, and that translates directly to roughly 1,000 qubit. you can have roughly 2 or 3 lines per qubit is sort of usual sort of, at least for superconducting qubits, that's a usual transformation. And it has a huge room for the payload also. It can actually support much larger weights than our standard systems. So in that sense, it's in one piece. You can sort of, if you just take the technology you have and supersize it, it's able to sort of support that in this system.
And what about dilution fridges for other technologies, other quantum technologies? You manufacture those also, or it's only for the superconducting ones?
Well, anything that operates in the gigahertz range needs cryogenics. So I think all the tools we are doing, they are, so I think spin qubits at the moment are at millikelvin, but they might have the opportunity to go up to higher temperatures, like 1 Kelvin. But that still means that you need an infrastructure like this. Then there's superconducting, there's Majorana qubits. Even photonics, to some extent, need cryogenics because they need a fast single photon detector, and that, of course, also requires cryogenics to make sure that you have good signal conditioning.
So, sorry, one more question. When you actually get this device and you fit your chip into it, do you need certain site-specific customizations, or it's all ready to go?
No, so of course, at this stage, we focus a lot on the cryogenics, and of course, we also do signal conditioning, but of course, we are not that deep into the customer's technologies. Of course, they have a lot of adaptation. As you said, if they have a chip, they need to have sort of some kind of chip holder, some breakout that connects it to the wiring that we might provide, or they have some special wiring that they need to sort of add into the system. And then, of course, at room temperature, there is, of course, at the moment, the need for control electronics that also is needed to operate the chip itself. And that is something we don't provide. I think there's other talks today. There was a Series instrument that also had a talk. So I think we provide, I think we usually say between the chip and room temperature interface, that's our regime, that's the cryogenics, and that we try to make as complete as possible. But the users still have to put in a lot of their own technology and knowledge into the systems.
Okay, thank you.
Thanks.
Any more questions?
David, thanks for an inspirational presentation there. Andrew Briggs from Oxford. There are other components that you may want to have between the room temperature and the device, things like Josephson amplifiers and so on and so forth. You already showed one amplifier that you provide. Do you have plans for providing any of those? And I suppose one of the biggest questions will be when the day might come that a lot of the electronics would be done at low temperature, thereby reducing the need for these gazillions of wires coming down from room temperature. What's your sort of vision for the future?
No, I think that's a good point, that of course, this system we have here, the platform kit, of course, with brute forcing today's wiring and technology, it's only ready for around 1,000 qubits. So there is, of course, technological development needed from the technology side also. And there, of course, miniaturization of components, for example, but especially active logic at cryogenic temperatures. That is, of course, moving the interface closer inside the cryogenic sphere. And I think that will go in stages. The question, of course, is that logic today, at least what I see the state of the art, it is quite power dissipating still. So that, of course, means that you will still have signal path from some temperature level to another. So you will still need a fairly large signal path infrastructure. But it might become easier and become less demanding. And of course, the amplification of quantum data, so this Joseph amplification or the parametric amplifier, I think that is things that is very hard to get away from. If you want to do serious quantum computation, you need single shot readout. And that means that you need devices that are sort of close to quantum limited. And I think that is very hard to make much smaller, but I think you can get closer and closer, and maybe in the future even those devices can become more integrated into the system. But I agree with you that there is for sure, it's going towards the center in that sense. But I think you still need a fairly large cryogenic infrastructure, even if you put the logic inside.
Thanks very much. That's very helpful.
Thank you so much, sir.
Thank you.
Yeah, thank you. Now we'll continue with the earlier panel discussion which was discontinued. So I request the session chair and the panelists to come on the dais.
I welcome the panelists back. My apologies for the disruption. So we'll continue with the panel. I think we have our next speaker, Dr. Natarajan Venkatachalam, SETS Chennai. May I request you to make your comments very briefly?
Good evening, one and all. So let me quickly brief the experience I had in my previous experience so far. So I've started this error correction, pertinent to the topic in 2012. 10 years back when I was a postdoctorate fellow at University of Bristol. Then I've been assigned to develop error correction software for different QKD systems, which are lab-based systems. There are, it is a field-based QKD systems and free space including. So then I started, it's basically, I come from the applied science and then mathematics. So I know a little bit of how the error correction works. I thought it's just flipping the bit and you will get corrected. So that's an understanding I started. Then I started building the algorithms. It's already coding theory based algorithms are well established in classical sense and tried to apply it. But it didn't work out. Then somehow I managed to get it for 80% or 90% for a different lab level QKD setup. Then moved to a field, their experience is different. These algorithms didn't work in the field. Then again the scenario in the free space is altogether is different. These algorithms didn't work out very well in this case. So the scenario is different. The same algorithm where it is basically algorithm is a deterministic set of procedure. It's supposed to work and react in the same sense in all these things. But it didn't happen in this kind of quantum setup. I'm talking about only communication. Similar thing, it's applicable for computing as well because the scenario is different. Then I've been doing a lot of studies how could be it possible. Then I read an article which states about information is no more logical, it is a physical phenomenon. So information is, there is a paper, interesting paper, information is a physical phenomenon. So then I realized that it's all the treatments which we do in the algorithmic level, it's an error correction or it's applying a quantum algorithm. It is not in a logical level of understanding where computer scientists do. It's more where we connecting to Professor Apurva mentioned, it is a physical phenomena which resist on this system. With our logical access, it is very difficult to manipulate the things. That's what I realized and understood. Then I moved to little closer when offline process to a computer to a, another hardware, FPGA, which more close to the the quantum optics. Still, we couldn't achieve the much things. Then I realized it is more of whatever the processing, in the software processing we do, it is all passive. It is a passive treatment, we treat these bit errors. It's nothing to do with quantum phenomena. In fact, I question why you call as a quantum error correction. Because everything is, all these principles are coding theory based principles, which are already evolved based on the classical systems, which are logical qubits. It's nowhere connected with the physical qubits. Then how can we call it as a quantum error correction? Because you apply logic which are after the measurement. Once you measure that, then all these properties of quantum is dismantled, then you becomes a logical qubit. It's like your classical one. Then it's not applicable, you call, so error correction for a quantum system you can call. Because I'm not using any quantum properties to correct the errors. Right? So that's the sort of understanding, but when you go into the quantum world, there it's like more active way of correction. That's where all the integrated things come into picture, where you correct more errors. And also there is a fancy you call, now long back people started using smart systems and smart phone or smart things. Now you started using Q, quantum machine learning and quantum systems. You all, everywhere the Q is being added. But it's not an easy job to do, I believe. Because the developer in a computer scientist, at least to have a knowledge of the physical phenomena, unless you cannot define a proper system. Because you see a traditional computer which works is application level and the controller level, which maybe includes all compilers, drivers, other stuffs, and the quantum hardware level. But my feeling is that it will not work in the quantum systems, because definitely developer have a certain level of knowledge of how this underlying qubit topology and qubits works. So let me stop here and over to.
Thank you, Dr. Natarajan. We will go to the next speaker, Dr. Gautam Paul, ISI Calcutta.
Thank you. So I primarily work on quantum information, particularly on entanglement-based protocol, their design and analysis, and also on quantum cryptography and quantum error correction modeling. So coming to the topic of this panel, quantum algorithms and quantum error correction, so I will make a few relevant points. First of all, there is a hype that if you move from classical to quantum domain, then you will have high level of parallelism, then there is quantum supremacy, and then basically you will speed up all algorithms. So that is not true. So first point is that because of quantum parallelism, not all classical algorithms cannot be optimized. Okay, so that's case specific. The reason is that quantum measurement collapses the superposition state, and in spite of beginning with parallel inputs, parallel processing and all that, ultimately you will have a single output, right? So you need clever way of manipulating things, and that is why it connects to what Anirban Pathak told, that there are very few, why there are few quantum algorithms, okay, in spite of so many research. So if you look at the publications, every day you will see that many new classical algorithms are being developed. But quantum algorithms you can count in your fingers in last 30 years. Okay, so that's one reason. Second point in quantum algorithm is that mostly the speed up that we get is in terms of search or optimization sort of algorithm. That's why people are keen to use quantum machine learning or quantum application to finance and stuff like that, because a lot of optimizations or search problems are involved there. In fact, any optimization can be modeled as a search problem, right? So this quantum search improvement over classical search, that is being used here. But the main problem or the main bottleneck in using quantum optimization or quantum search whether it is finance domain or machine learning applications or any other thing, is the encoding and decoding. So you need to have proper quantum encoding of the classical inputs, and then after that decoding. So unless that is done properly, you cannot immediately plug and play any quantum optimizer to solve any classical problem. So that's not what is going to happen. So, and the third point regarding quantum algorithm is that entanglement plays a key role in efficiency. So if you can use quantum entanglement to your benefit, then your quantum algorithm may give better results. So these are the 3 points, particularly on quantum algorithms. Then on quantum error correction, one fundamental thing that we should remember, that in classical error correction, mostly we are focused on the communication channel, right? Because we assume there is no error in the computation that is happening, or there is no error in the memory. All of the errors are happening in the communication channel. So you probe the channel, you estimate the channel noise, and you devise a suitable scheme to address it. On the other hand, in quantum domain, errors are happening in quantum channel, errors are happening in computation, because quantum gates or quantum circuits, no matter what technology you are using, each of them have errors, specific errors. So you need specific error models in order to address that. And in quantum memory also there is error because of decoherence and stuff. So you have to keep on correcting the errors and to maintain the state. So quantum errors are omnipresent, and that's why we need different strategy to address them. I think this isolated way of addressing quantum errors in different segments that may not stand in future. We may need to build a holistic approach, like how to address, how to correct the errors in the system, the overall error in the system, right? So that is one point. And the last point that I would like to mention is that in all domains, be it classical or quantum, the basic philosophy of error correction is redundancy. So if you have certain bits or qubits, you add some more bits or qubits in order to project it to a high dimensional space, and then you know that, okay, if there are errors, you will be still around the message vector so that you can decode back to the what was originally sent, or the original value was there. Now the problem is in classical domain this works fine. Though in quantum domain this is the basic method that is used, there is one problem. As you are adding more and more qubits to the system to correct errors, you are actually increasing the error also, because every qubit is associated with its own error. So we call it the crazy kids problem. So in a room you have put some crazy kids. Now you are adding some more crazy kids to stop them, but the new kids that you are adding, they are creating their own noise. So there is a trade-off. Just by increasing the number of qubits, you cannot correct error, because it's kind of having double effect. It's correcting the errors of the existing qubits, but it is adding errors on their own. So it's kind of domino effect. And when do you stop? How far do you go? That is particularly the reason why we are stuck at the noisy intermediate scale quantum era, and scale up is really a problem, particularly because of error correction. So right now if you look at the curve, so if you plot the number of qubits in the horizontal axis and let's say the error correctability or the efficiency in the vertical axis, you will see that there will be a tip-off point. So beyond which, just increasing the number of qubits up to few hundreds more or few thousand more do not work, right? Because of the error correction challenge. So that's a very key point that we should remember, and we should all work towards actually increasing that tip-off point so that more and more qubits can be used in practice. Okay, so with that, I will stop.
Thank you, Dr. Paul. I think wonderful explanation of how error correction really has other problems associated. So I'd like to move to the next speaker, Dr. Venkat Subramaniam from IBM.
Thank you so much. So I'll be brief because I think I'm the last speaker for the day. So I'm going to just, dwell upon where we are today, right, in terms of implementing some of these things. So there are three things. One is error. We've all talked about error correction, but as you know, rightly pointed out, in today's systems, we do not implement error correction, right? Because there are too few qubits out there. There is nothing, you know, you can actually correct at this point. But we do look at error mitigation, right, as one of the things to use to reduce the error, right? And recently we demonstrated that on some of our large systems, we are able to achieve the 3 nines fidelity, which is 99.9, right? So the 3 nines, which enables you to still have large number of circuits run on your systems, right? So for example, we are targeting that by next year, we'll have this challenge of 100 cross 100. What does that mean? 100 cross 100, 100 qubits, and being able to build a circuit of 100 depth, right? So, which means, you're now getting into a regime where you're able to look at problems in a new way, which is, which is beyond classical, right? So today when I talk to youngsters or industry or anybody, we think linearly, right? We are not able to think beyond our classical systems. I ask, what problem would you like to solve? And you come up with a extension of what you are doing today, right? We haven't really started thinking in the quantum sense, right? We have not started thinking about how can we, solve some unsolved new problems. We are just thinking about the extension of existing problems, and we are limiting our thinking by that, right? But one of the things we are doing now is, now we have the 400 qubits. Later this year we'll have the 1000 plus. Also, we are going to get into an era where we are modularizing the chips, right? Which means you're able to interconnect chips, and we'll get into 4,000 plus qubits by 2025. So all of this means that, this is the time for us to actually start thinking, and as a country which has a very strong base in software and algorithms, it is time all of us actually took advantage of the systems which are here to start thinking beyond the classical problems that we are solving, and to think of, what are those big problems which we can solve, because we are at a point where, at an inflection point, where I think we can do it in the immediate near future. So, thank you.
Thank you, Dr. Venkata Subramaniam. I think we have finished with all the panel speakers. So I don't know whether there's time for maybe a couple of questions from the audience. If there is something, then we can address it. So maybe I'll put a question with, I think all of you are very well-known people in the experts in this domain. So, I mean, from the applications community, what kind of problems do you think, should be tackled first, because definitely, as all of you all have mentioned, problems which require greater search space is something which is needed. But is there something which you can give as a takeaway message for the application developers?
We have started looking at some machine learning problems, right? You take classical on one side, and it has some accuracy. Let's say you want to achieve 90% accuracy on that task, right? Which is what classical is achieving. What we are observing is that using quantum, first of all, we require lesser training data to achieve the same accuracy. Okay. Number two, we are also able to train models faster. Okay. So these are very early indications. I'm not saying this is quantum advantage per se, but what this means is even on the low qubit devices, you're getting into a regime where you're seeing small empirical advantages on specific tasks, right? So requiring less data is a big achievement, right? So all of these point to us saying that, this is the time for us to tackle some of these problems, especially in machine learning where quantum naturally, works in the higher dimensional spaces. So this is an opportunity for you to start looking at those problems, and as the number of qubits increase, as error mitigation and in future error correction happens, you are able to take advantage of this. Of course, we all want that, we have thousands of qubits and millions of qubits and all of that, but we don't have to wait for that. Today you can start, and you can start observing some of these very exciting developments which will encourage you to, go deeper.
Anybody has? Yeah.
No, I think, yeah, other than machine learning, I already mentioned that particularly search problem and optimization problem, which also has intersection with machine learning.
So my view is it's more may not be for an immediate future. I look for different segments. It's for not long term. So mid term, it looks like quantum accelerator kind of thing, wherein you cannot afford for entire computational to be happen in the quantum system, but certain operations that I can classify in with respect to the any type of domain, it can act as accelerator, which accelerates the computing, wherein if you identify this problem is suitable for the quantum domain, wherein you can offload that problem, it makes an accelerator. So that can support very well with the existing computing ecosystem.
Okay. So you're looking at hybrid kind of systems?
Yeah, so that, more or like hybrid, but certain offloading. Already we have an offloading, computational offloading for cloud, other things. It's kind of another system, where subsystem which supports with the classical system, wherein you accelerate certain classified computing process.
Okay, fine.
Yeah, I'll give 2 examples. For example, when we do Monte Carlo simulation, we need the random noise. So we just checked in couple of 2-3 examples, like for example, the simplest thing that is taught to us, that if you look at an area of a circle, pi r square, if you use random numbers, you can actually find it much faster. In fact, we checked that the noisiest IBM quantum computer gave the fastest answer to the area. And we have checked in a couple of other examples. I know I would not be mentioning because quickly we will be writing that also. So this noisy quantum computer can be effectively used. Second way, see, whenever we look at any quantum level, every quantum level is not sharp. Intrinsic noise is there as a line width, which implies nature has error built into it. And how do you take advantage? So this von Neumann measurement, which collapses the state, instead we have something called unsharp measurements, where a certain state with certain width around it, you use that kind of basis is available called unsharp measurements. That way, for example, you don't have to take 5,000 ensemble averaging to get the answer. So you can really make use of the natural noise that comes out of quantum computers to actually converge on good answers. In fact, very recently we found that in some sort of search algorithm, particularly and let me not get into details, this unsharp measurement gives you very good answer. So you take advantage of noise. Noise is not all that bad.
Thank you. I think wonderful to have all the panelists speak here, and on behalf of the organizers and C-DAC, I'd like to thank all of you, and I hope all of you have enjoyed the session.
Thank you so much, everyone. Now I request our session chair to felicitate the panelists. Now I request Colonel Ekinath to felicitate Dr. Rajendra Joshi. Thank you so much, sir. With this, we conclude the session.
Good evening, everyone. This is the last session of the two-day symposium, which is on standardization. The session is chaired by Colonel Ekinath. To commence the session, I would like to invite Mr. Manikandan K, Bureau of Indian Standard, to share his thoughts. He is connected with us online to deliver his talk.
So I hope my screen is visible now.
Yes, sir, it's visible.
Thank you. So let me thank C-DAC at the outset for giving me an opportunity to talk about standardization in this crucial area. So, I know many of you are, so all of you are experts in the domain, which is quantum technologies, but I am not. My area is standard development. So I have been working in this area for quite some time, standardization in general, but not specific to QC or quantum technologies. So in general, standards, they are always best tool for both governments and industries and for all stakeholders. Because it provides a solid foundation where a lot of innovation can happen. And these are some general benefits of standards. Like it captures the best practices and it captures the wisdom of domain experts in the area. Then basically standards, if you look at any area, like even in the emerging areas like AI, IoT, so it provides a framework where a lot of innovation can happen and people can, the developers or the implementers can get the confidence that they are working within a safe environment. And when it comes to quantum technologies, again here standard standard can play a critical role in the sense that it can ensure compatibility among different quantum systems and applications. And if you look at any specific areas like quantum communication, be it quantum communication or computing, it plays a lot of, it has significance in the sense that in the area of quantum communication, the standards can ensure that the quantum states are prepared and measured in a consistent way, in a standardized way, or in terms of computing. These quantum computing devices, as I understand, are highly sensitive to environmental conditions. So the standards can ensure that these devices are operated in a reliable manner. And if you look at quantum internet, internet is all about protocols, right? So we need not to say, it goes without saying that a standard has a critical role to play, even in terms of, even if you look at the cryptography, quantum cryptography, post-quantum cryptography, again, these are standardized protocol and it has standards, everything is done on the basis of standards. But if you look at the trend in the what kind of standards are being developed at international level. By the way, I'm working with Bureau of Indian Standards, which is the National Standards Body of India. And BIS is the nodal body, member body of both ISO and IEC. So in a way, I'm involved in the standardization, the technical committees where the technical committees related to quantum technologies within ISO and IEC. And the current practice in these committees are I'll share the details of the committees in the coming slides. But in general, the current practice is developing the foundational standards. When we say foundational standards, it's like developing terminologies, taxonomies, concept systems, or reference frameworks. So many a times in a single glance we feel what is there in a terminology, but it's the most important part of any standardization effort, because how do we communicate without terminology? Many people use different terms or different vocabularies or different jargons within their domain or within their office or within their industry consortia. But when we communicate the message with someone else, they may be using different terminologies for the same stuff, or they may be using same terminology for different stuffs. So in either case, the standardization really is very important, so that the same understanding, it creates a common understanding among all diverse set of stakeholders. It is same with the case of concept systems. It creates, if we can create a conceptual framework, what does it mean by a quantum system? Yeah, maybe for any, it can be application specific or it can be a generic kind of. In a typical quantum system, what are the major entities that should have, how these entities talk to each other, what are the relations, interdependencies. So these standards like concept systems or reference frameworks brings a lot of clarity on these questions, like the different elements, the interdependencies, how is the information flow, how it is done. All the details are captured and described in a standardized manner in such standard. And trustworthiness is another important area on all these technological domains, to ensure that how reliable or how trustworthy, of course reliable is not trustworthiness. Trustworthiness is going to be a major umbrella under which all this reliability, security, privacy, many things can be covered. So that's another area where these standards are being developed. So that's the current focus of these SDOs. SDOs mean Standard Developing Organizations. And so, okay, in the coming slides, I just captured some of the standard developing organizations and the documents and the standards published or being developed by them. So I'll just skip through these slides. Like at C, they have a group or ISG QKD on quantum key distribution. So there is a list of projects they have done or being developed under ETSI. The list is here. Their main focus is QKD and IEEE. So they have published a lot of standards. Even the list is here: software-defined quantum communication, post-quantum quantum network security, or standard for a quantum algorithm design and development, so and so, hybrid quantum versus classical quantum, and quantum computing and simulation energy efficiency. And similarly, there is another group, Internet Research Task Force, associate body of IETF. They also work on, their focus is on quantum internet. Their focus is on quantum internet. So, here there is one working group within ISO IEC. It's a joint group of ISO and IEC. They have a group on quantum information technology. So by virtue of my association with BIS, I could attend some of these meetings. So they have already identified a few projects which are progressing. but they have not published any standards yet. Some are at the final stage. So these are some of the projects under this working group. So basically, if you look at this group, there is something called system integration entity. So this is like a developing horizontal standard. They may not be focusing or developing standards or for any verticals, but it's like a overarching standards they focus on, which I covered, the reference framework that I covered in my earlier slide. So they develop foundational standards basically. And there is another group within IEC, which is IEC SEG 14 on quantum technologies. This SEG stands for Standardization Evaluation Group. Again, this group doesn't not mandated to publish any standard as such, but this group will be doing that initial study, the landscape study. What is the QT landscape? What is the ecosystem? What is the market drive? And what are the current priorities of industry and stakeholders or the consumers or the government? So all these requirement they study, review, study, and finally they submit some recommendation to the top body in IEC, based on which they will initiate the standard development through any of the existing technical committees or by creating a new technical committee. So presently, as you can see at the bottom portion of the slide, like they have 4 working groups to look after different, to monitor different different areas within this quantum technologies, like market, use cases, research development, then standardization activities. Then ITU, again, ITU has, ITU, their focus is mainly on quantum communication and networks. So their focus group, QIT4N, the objectives are listed here: to study the evolution and application of QIT4 networks, to focus on terminology and use cases for QIT, and to provide necessary technical background information and collaborative conditions to effectively support QIN, and to provide an open cooperation platform with ITUT study groups and other SDOs. So these are some of the recommendations or technical reports released by ITU so far on quantum networks or and communication. So if you look at all these, okay, let me also go through the next next slides. So in BIS, we are comparatively new to this area. So we in Bureau of Indian Standards, we initiated the standardization in the area of quantum technologies last year by creating a panel, LITDCP5, on quantum. The panel title is Quantum Computing, but if you look at the scope, it covers broadly covers all aspects of quantum technologies. And this panel is also it also functions as the national mirror group for ISO and IEC, corresponding ISO and IEC committees. So these are the this is the composition of the committee. So we have held a few meetings in the past, and the experts and the panel identifies some of the priority areas to be looked after from a standardization perspective. So it goes like this: quantum hardware, quantum QIT terminology, then benchmarking against classical computers, then quantum computing related services and hybrid computing. These are some of the areas identified by the panel. And the plan is to explore more about each of this area and review and do a study on the relevance of standards. And because as you have seen in the previous slides, many of these standard developing organizations, they have already published several standards in each of these areas. And if you look at again, some of the areas are really overlapping, because if you see ITU has a standard on terminology. Similarly, ISO is also working on as a terminology. Whether the terminology given by ISO and ITU, are they consistent? Sometimes it may not be, right? So similarly, many of these standard developing organizations are working on same subject. Of course, the experts cannot be similar. There may be some common members, but more or less the experts involved in writing the standards may be different, right? So as a country, our priority should be reviewing all these efforts by the global bodies, and wherever we can, we should contribute. We should really engage our expertise and our experts in all these technical committees and working groups, and so that we won't miss the chance, because this is the right time to participate. And as India, we have what to say, some needs or maybe our specific requirements. So if we can engage with all these technical committees and working groups in time, we will be able to communicate our specific requirement that can be addressed, or our specific concerns can be addressed in the international standards. And once they publish, we can identify and adopt the right standard. So another, in terms of standard development, I would like to emphasize on this work, potential overlaps and potential, what to say, I'm not getting a better word, but let me say misalignment, because many a times these different technical committees develop standards on same area or similar area, which may not be coherent always. So it's our responsibility to review the work in time, and wherever such inconsistencies and misalignment is there, we should highlight it, because we are going to, we may be adopting at the end of the day all these documents. So that is the present standardization landscape, and that is about where we should focus. And within India also, there are different bodies. BIS is developing standards, and DOT, DEC is also developing standard. So we have a mechanism to collaborate. So I would request all the experts gathered here to really, what to say, dedicate some time for the standardization activities as well, because it's really important in saving time and saving a lot of effort, saving a lot of time and or investment. We can save a lot of, bring a lot of efficiency in the system through standardization. So that's all from my side. I think I'm done. Thank you.
Thank you, Mr. Manikandan. Please be with us. There is an update. Mr. Gurumohan Singh, Joint Director, C-DAC Mohali, will be the session chair for the panel discussion. And I would like to call Dr. Harish Sahu, SAG DRDO, and Dr. VR Chele, Director, Quantum Technology, DOT, to join the dais and take forward this session.
Hello, am I audible? Okay. So our next panel speaker is Dr. Harish Saus from SAG DRDO. Dr. Saus, please continue.
Turn on the presentation. Switch to presentation. Just go to presentation, it will come. ठीक है मेरे ख्याल से हो गया था अभी।
Okay.
Yeah. Sticky क्यों फट गया? I don't want this slide to come. Just come here. Maybe we can do it once more. It's stuck over here. एक बार उसको मेन्यू करके वापस दोबारा क्लोज करके थोड़ा सा करिए from beginning. So good evening everyone. Thank you Dr. Anindita and Dr. Today is the last session, second last session, and I will be covering this. So my agenda of my talk is that effect of this quantum computing on cryptography. So in that we will see the effect of quantum computing on both symmetric and the public key cryptographic scheme, and what are the possible countermeasures which can be taken. And the next part of the talk, I will present this quantum safe cryptography and standardization status that has already been covered, so I will skip that. So let's see the effect of this quantum crypto on quantum computing on cryptography. So first we will see the impact of this on symmetric key cryptography. So in 1996, Love Grover has given a quantum search algorithm which can reduce the, which can give the speed up of quadratic speed up which can give. So for n item, it can search in square root of n time. So that thing we can use as a key search in symmetric key schemes. So if we want to search exhaustive trial of the keys, then in case of AES 128, the key space is 2 power 128. If we do it classically, then we need to try 2 power 128 keys. But if we have a sufficiently large quantum computer and this Grover's algorithm with you, then we can do it in square root of that space, that is 2 power 64. So that is a significant reduction in the effort which require for brute force. So what is the possible countermeasure? So the simple countermeasure is that just increase the key size, double it. So doubling the key size will solve our problem. So we can use whatever cryptographic scheme we are using, just double the key size. So in case of AES 128, if we feel it's a secure, then just double the key size. So that will be secure against quantum attacks, basically based on this Grover's algorithm. So in symmetric, there is no big problem there. Just double the key size, you will be safe. But in case of this public key cryptography, These are the famous popular public key schemes, RSA, ECC. They are based on some hard problems, which are mainly factorization and discrete log problem. So in 1984, Peter Shor gave this factorization algorithm. So using that algorithm, these tasks, which are this integer factorization and the discrete log problem, which are shown here, so which are hard for a classical computer, but these are easy for a quantum computer using Shor's algorithm. So if you see the complexity, multiplying is easy in classical as well as quantum, but factorization of large number is very difficult for classical supercomputer also. So the complexity is exponential in terms of number of bits. But for Shor's algorithm, it is polynomial, and polynomial is very fast and easy. So if you see the estimate by the Born, in which if we progress in the classical computer domain and we increase our this computing power, we will be using supercomputer and the other classical developments. So if you see for this 2048-bit numbers factorization problem, in 2024, it will take 10 to the power 12 years classically. And if you go to 2042 also, this will take 3 into 10 to the power 8 years for a classical machine to factor this kind of number. But if we have a small quantum computer with thousands of qubits, then we can do the factorization of this 2048-bit number in minutes. But for that, we require a large-scale fault-tolerant quantum computer with sufficient qubits. So this poses a threat for this RSA kind of cipher, which we use in our daily life for key exchange. And if you see this Shor's paper, this paper has given algorithm for the discrete log problem also, not only integer factorization, for discrete log also. So in discrete log, finding this x is very difficult for large numbers. So, and this discrete log problem is used in Diffie-Hellman and other public key crypto systems. So we cannot use this classical public key crypto system, which I mentioned, because if we have this large quantum computer and the Shor's algorithm, then we can break those kind of ciphers and it can reveal the secret. So effect of this quantum computer on crypto can be summarized in this table. So public key, which we are using, will not provide any security at all. If we have a large quantum computer, then Shor's algorithm can break all of them in some minutes. But in case of symmetric, as I told, that the key size just need to, so if we use these Grovers, and then the effective strength will be half of the key size. So if we are using 128-bit key, then strength will be 64-bit key only. So the solution is that you just need to double the key size. But in case of this public key ciphers, we need to shift from them, because because increasing the key size will not solve the problem in case of public key cipher, because the algorithm is polynomial time. So, and we cannot think that, okay, today we don't have a large quantum computer, so we can be like relaxed, because these algorithms, Shor's and this Grover's algorithm were given in 94 and 96. After that only this quantum computer development has actually begun, because the idea was given by Feynman in 82, but after 82 there is no effort for developing this quantum computer. But after this Shor's and this Grover's algorithm, quantum computer development started. In 1998, if you see, the 2-qubit quantum computer has been developed by MIT and UC Berkeley. But after that, if you see the progress, it was 24 years ago, we have 2-qubit quantum computer, and as of date, this IBM has already developed 433-qubit device. So progress is tremendous, and it can happen in the same fashion that maybe some rapid or some different technology comes and we can have a large quantum computer with millions of qubits also possible. Some breakthrough technology, this whatever we are discussing is this semiconductor and this technology we are discussing. But someone can come up with entirely different technology based quantum computer and which have sufficient large quantum computer, then there will be a problem. And in this context, Michael Mosca, professor in University of Toronto in Canada, has given this Mosca theorem. What it says is that when we should worry about our cryptography against this quantum computer, so when this X, Y, Z are defined like this, X is the time which you want to make your information secure. How much time you want to keep your information secure. X is the time. Y is the migration time. Suppose if you want to change from some crypto to other crypto, you are taking Y years to migrate. So, and the collapse time Z is the time when we have a large scale quantum computer. So suppose this X is that, suppose some secret I want to keep it for 20 years and I take 1 year for migration. So X plus Y in my case is 21 years. But suppose in 10 years, if we have a quantum computer or in 15 years, then there is a problem. Why? Because I want to keep those secrets for longer duration, but collapse time is already happened. So if our security self-life and this migration time is more than that, this collapse time, basically the quantum computer available time, then we should worry. So in case of strategic or defense or some important government communication, the security shelf-life is in years. So in those cases, we cannot use those cipher which have threat from the quantum computer. So we need to worry on those cases. So what is the solution? So for this public key cipher, which are used for this key exchange in internet or everywhere, so for that we need a replacement because they will not provide security at all in case of this quantum computer. So we need a quantum safe cryptography. What it means is that whenever we will have a large quantum computer or maybe some classical advancement, our crypto will be secure in both the cases. So classical solution is called post-quantum cryptography, in which this public key cipher are replaced by newer ciphers which are based on hard problems which are hard for quantum computer also. Earlier, these problems of integer factorization, discrete log were harder for classical computer, but not in case of quantum computer. So what is the idea here in this post-quantum cryptographic scheme is that we should have a problem-based schemes which are harder for quantum computer also. So there are various lattice-based problems and code-based problems. On these problems, we can design our systems, post-quantum systems. And in place of this classical public key schemes, we can use them. So these are basically this lattice-based, code-based, and these systems are basically public key kind of system only, but based on some harder problems which are hard for quantum computer also. And other domain is called quantum cryptography, in which we are using quantum photons for our communication or distributing the key. So for this post-quantum cryptography, NIST has started this competition for standardization to replace those classical public key ciphers. So this started the competition for standardization in 2016. And that time, initially 69 candidates were submitted from variety of domains like lattice-based, code-based, and different. And after first round, there were 26 candidates, and after third round, there were 7 finalists and 8 alternatives. So as of now, the status is that last year in July, NIST has selected these algorithms for public key encryption of the key establishment mechanism. So Crystal Kyber, a lattice-based crypto system, has been finalized. And in digital signature, we have 3 schemes. 2 are based on lattice, and 1 is based on hash. So these are finalized for standardization. And 4 other algorithms are also taken, which will be evaluated till the 4-round results. So they are under consideration still, and they are based on code-based cryptographic schemes, and 1 is based on elliptic curve isogeny. So this, so we have variety of systems. Like some are based on lattice-based, some are based on code-based and elliptic curve also. So it is expected that in 2024, NIST will roll out with final candidates which are standardized and ready to use for communication in place of the classical public ciphers. And this PQC candidate or other, in defense and some academic institute, we do designing and analysis of this kind of PQC systems at our country level also. And we do analysis of this post-quantum candidate also, which are being evaluated in this NIST competition. So, so the quick solution is that instead of this public key cipher, we can use those standardized PQC candidate in future after 24. Then we will be safe. But the condition is that these problems, lattice-based problems like shortest vector problem and other problems, which we are assuming as of now hard for quantum computer, but maybe after some time or some years, someone can come up with efficient quantum algorithm to break them also. But that is very least likely. So other ways, this quantum key distribution, in which what we do is we just send some photons from transmitter to receiver to establish a symmetric key between two parties. And this thing is based on the quantum physics laws. So it provides us absolute security. So whatever advances you do in the quantum computing and classical computing, this quantum key distribution will not affect it. So in this QKD, what happens is that through this optical fiber or free space, we send photon from some sender to receiver, and based on the encoded information in those photons, we generate a common key, and that is used for our symmetric key. So here, if you can see, that simple protocol is shown, that we are encoding our information in photons polarization, vertical, horizontal, or plus 45, minus 45, and then sending it to receiver, and receiver measure, and based on that, we generate some key. So in this QKD, recently, last year, DRDO has demonstrated in Uttar Pradesh, between two cities of Prayagraj and Vindhyachal, 100-kilometer fiber is laid there in the field fiber cable. We have demonstrated this QKD, and we have retrieved a key rate of kilobits. And similar experimentation and demonstration has already been demonstrated by other institutes like C-DAC and IIT Madras and CUNY Labs. So the things are happening very good QKD progress in the country. And in case of free space, ISRO has demonstrated this 300-meter free space QKD. And the country is planning for a satellite-based QKD, because this fiber optics has limitation of some 100 kilometers or so. So for larger distances or countrywide coverage of this thing, we should have satellite-based QKD. So in which direction also our country is progressing. And I think C-DAC is also having floated a project on satellite-based QKD. So Dr. Anindita has also proposed a project on satellite-based QKD. So various groups are working, and we are doing good in case of better than this quantum computing domain. I can say that we are not that good, but in case of this QKD, progress is significant, and we are almost catching up with the world level progress. So this standardization process has already been covered earlier. Just I want to focus here this ISO IAC. So in which we are interested in the QKD security specification and the testing. So whatever this QKD protocol we are claiming, it is doing the same thing or not, some other malicious things or something, and we try to attack that system, basically side channel, because theoretically this QKD provide security, absolute security, but while implementing, due to device imprecision or some malicious things, something can go wrong. So before deploying this kind of system in strategic things, we should security evaluate them and then use for secret purpose. So, thank you. Okay.
Then later.
How it can affect the coming years in public cryptography system in coming years. Now we have our next panel speaker, Dr. V.R. Chelle, Director, Quantum Technology from DOT. You can start, sir.
Good evening to all the members who are here attending to visualize our presentation. I should thankful to C-DAC taken a lot of pain to conduct the workshop. Really, we know we are planning for last 2 months. Still, we could not conclude the day. Finally, we concluded the March 28th. We know the pain and difficulty challenges, because each point has to take and they have to carry the regular work also. That is a great job. no limit to upload them. Anyhow, it is already covered most of the contents by previous two speakers, Mr. Sahu and Manikandan. Still, we have slightly different role also. I will explain shortly. Please, next page, next one. Next. This is already standardization is a definition already covered, Mr. Manikandan. Please go next. In this process, just go next. We do slightly different. We do consultation, the same thing to distill the wisdom of the industry, the members and the users and research organizations, academia. We consult everybody. We share. Next page. We consult everybody and take their opinion and their feedback and incorporate the changes after concluding the final acceptable level of draft for all the members. Then we bring the next stage is the DCC meeting. Then after only it will get approval. Then we notify the document. The same thing. In this document, how the TEC make a slightly different. We participate the standards organization as a contributor. Like ITU, we have many contributions as notified in the ITU also standards. We means not only we, the industry, all Indians here, we used to invite the members. They all collectively we collaborate all the contributions. Then we send to the participate in the ITU and discussion. They do discussions. Average it will take 4 years. Their time period. They will get approved. An average 10-15 standards will be notified every 4 years in ITU. Next is the 3GPP also. They are participating. Now the release 18 is under finalization. These are the main two areas, and now we have started IEEE also participation. But ISO we are not participating, but from BAS they are member, they are participating from behalf of country. As next is that whatever standards we make, we notify the document. Then after that TSTP, test standard, test procedure also, we draft the procedure also. Most of the documents we adopt the standards which already is available, like ITU, it's ITC, 3GPP, IETF, all global standard bodies. We adopt most of them, and very few parameters we change as per our requirement. Some we may drop also, depends on the severity of the parameter, which it doesn't make any sense, so we drop it. So next. We issue the two type of certificate. We do we participate the standards body also, including Indian standard body, TSD, SI also in telecom sector, and related ICT also covered. We are one of the contributor, and also we issue the certificate, two types of certificates. One is a voluntary certificate. Under the voluntary certificate, whatever we first initially we notify the standard, then called is a generic requirement. Under the generic requirement, and it is a type approval certificate called a type approval. And any research institutes, they apply the certificate. We call it is a technology approval. If the two more are the certificate approval is if a GR is not there, then industries they give the product as per the specification. We verify the in premises. Then we give the certificate type of certificate of approval. Then interface approval is only the interfacing functionality. Will verify the premises of the applicant, then we give the certificate. But today we are migrating towards this is one type of these are all voluntary certificates. But in the present JUM portal also, whatever telecom or ICT products GRs available, now we are making mandatory. Any procurement should be done only provided they have the GR certificate. If they don't have, if anything is not mandatory. The second one is the 2018 Telegraph Act, they have modified and introduced the test class mandate testing and certification program, under which all the telecom and equipment and related ICT, they are mandatory to pass the certification before import and for also sale in India. So this is under which we have the authority to control the standard products to import and sale, which with this clause it will enhance our market, restrict our market, but we should follow as per the WTO agreement, whatever non-technical barrier should be comply the WTO, and we are the one of the member, along with the BAS, we are also the member is related to telecom and related ICT products. We notify the any standard technical specification modify, then we get a query from the other members of the WTO country, then we will reply, then we also write the same if any queries are there, the standards implement other side. And for this is the one process. How the certificate process will be done. First, when we notify the standards, after notifying standards, then it has made under GR it will have voluntary. If it comes under MTCT, there is a one clause, MTCT we are not notified all the products. As on now, it is more than 70 plus products as notified. We notify, we give some time, 1 year or 6 months. Then after that is a mandatory to get certification before import or sale in India. The same way here also, many products also we have, after this certificate process, we have many products are also rejected because of the non-compliance and other reasons. And also we are under MTCT, there is a compliance clause is the one is the security requirement, safety requirement is to be complied, EMC electromagnetic compatibility has to be complied, the technical parameters has to be complied, and others means the functional parameters and also security parameters. Security as in now it is standards just some of the products are released, now it is yet to finalize the deadline for the compliance. Now the second part is that under this how to carry the test procedure. Test is that there are two methods. One is the premises we go and verify the equipment, then if they pass the test, then we will issue certificate. The second part is under MTCT, this is a different procedure where the labs will be designated. In the BAS also same procedure. If the BAS also, if they are designated also, it will be allowed here. For any lab to get a designation, first the NABL accreditation is to be taken. Next then will be designated in TEC. For the separate body is there, they give a designation. This is one of the opportunity to, we have to create the testing labs also, under which it is very essential they have the business, and also these labs will be useful for our country also, for research organizations and other product development organizations also, because this will enable them affordable to verify the products and get validate before the actual offer. Next. This is the which I already explained the procedure. When any product is notification, before we prepare a draft, after we generally we will see the product whether it is a really implementable TRL level 8. It should be 8, at least 8. We are not asking, but the expectation that it should at least 8. The product should be usable, and once the product is we also do POC also, proof of concept test also. If somebody innovators, startups come, they want to verify the product, then we facilitate the proof of concept. Once they qualify the proof of concept only, then they can go for real systems. Then under this, the procedure is a document. When we notify the draft, then we consultation, sub-DCC, the members, we invite all the industries. Industry is the manufacturing forum, we call. Then sub-DCC members, we invite all the academia, then research institutes, and various government agencies, PSUs. So who are involved in the related to product, so that we take all their opinions and the committee. Then we go final stage, one more stage, DCC Development Coordination Committee. That is the final consultation. After that, we will get approval, we will notify the document. That is the process we adopt here. Unlike the ISO, IEC, and the BAS, where technical committee will be there, technical committee will decide. But here is the consultation process. That is the difference. Can you go next? Now our strategy, planning is that already standards for QKD system has released 2022, and this is based on the ITU standards, Y.30818, there are 4 standards are there, and the ITC standards are there. Based on these 2 standards, we have some other standards also, but we are very few. Major contribution is taken from ITC and ITU standards. The other one is that for TSTP also under finalization, once this is over, we have seen in the market QKD, the C-DAC has developed, and they are under process of testing. The second one, QNU Lab. These 2 we have identified, and they are given a request for that certification also. It may get shortly. The second one is the cryptography system for classical as a post-quantum cryptography. Now it is under consultation stage. It may take maybe March, we will be able to release the standards. We are trying to reach totally industry, academia, and research organizations. If anybody missing also, they can convey to me. I can share the document. Further, their inputs will be taken into the document. So ultimately, the purpose of the consultation, wider consultation, will give minimum errors, which because equally important. That if you do wrong and improper standards, that will cause the severe damage, either maybe country or users or maybe industry also. It need not be one side. It can be any way. That is one. Next one is the QRNG also, which is a planned next after a cryptography system. We want to carry the QRNG. Then is the quantum computing components also. Then quantum AI system. These are only we have made a plan, but as an products mature only, we will bring the standard. Till that we will not. That is very clear. So next one is the quantum repeaters and also quantum sensing and imaging system also. These are the ideas. It may be slightly name changed. It depends on maturity level of the product. It may be differ in the same area. It can be more than one type product also. It can be brought a different name also. It depends on the conditions. And whatever QKD system we have developed only for 2 protocols only, we need to develop standardization for others also free space. But we are not seeing the mature products. That's why we are not come up. As and when it comes a maturity of any product, please all, if anybody knows also, as a users, as a OEMs, you can also intimate us that standards need to be revised or to be enhanced or new products to be, because we are welcome to all the users. And we encourage the standards is the environment where India, we were not so much serious earlier. Now it is very important, as Mr. Manikandan also has emphasized, the standards really make a comfort for the industry to come up the products and the certainty of the product get market access. Market access is very equally important for the survival and growth of the company. And as well as the proper product is equally important for the user prospectus, which he need not to be, he get a confidence on the buying of product. Is a more, he can visualize the he can use how can he use the system, the confidence between the user and the supplier, both will be increased. Ultimately, the trust level has to increase. That most important for any business system to be more sustainable and more economic. That is the plays major role. Then we can go next page. Next. And we have made a roadmap also we have made in the TEC portal. It is the document is available. You can have look into that. We under Telecom Technology Development Fund also it has been given input for the funding for the establishment labs, either academia or research, where we want to reach the government fund should be reach the maximum people. The industry, it should be anchoring by the either PSU research institutes to anchor the researchers, scholars, and the innovators who are keen to have development. The products, they should able to encourage them with a very nominal fee, and even many government has given recently the 5G test bed also. IIT is available where they given a SM is free only, and some institutes with a very nominal fee they made, which is facilitating the innovators to come forward, because ultimately the test equipment, test facility is equally important. Unless your development is known to you, whether it is fit in as per the standard development, you need to evaluate somewhere else. The test beds will be facilitated, and we also encourage and expect that C-DAC, one of the organization, which they can lead the test bed facilities for their consume for their internal use for research, and they anchor the PhD holders and other innovators to this area. It can be encouraged, and this environment also here, many this area around physical this area also people can utilize it. That we are expecting that they should come forward, and we whatever support and we inputs to be given, we are also coming forward to do it. So whatever testing certification procedure, when you draft certification, then lab designation, then validation. Validation we are not doing, the labs will they do it. If the lab facility not available, the lab has not come up, only the own equipment they are available in the manufacturers, then we go there and we validate it in that case. That depends on the circumstance, resource availability. We are making flexible in the scheme, so that the system, innovation should not stop. It should have to reach groom the innovators as well as the users has to get to utilize the facility innovation. That is our idea. Second, other one is we are international and national coordinators. We are giving input for with respect to standardization, and henceforth we are also idea in ITU and IEEE and other parts. Wherever the consultation is there in the standard quantum products also, we would like to invite all you. So we are identifying each product wise latest joint coordination committee for in QKD system also they created. They are going to further discuss in the ITU. I will, you can check in ITU also, you please registered, and March they are conducting meeting also. You can, whoever are working in QKD system, please join. And this will create a good, create understanding the standards and technology, how the global it is evolving, and how we can fit our innovation ideas can in this, or you can have more than above also, you can give the input in the consultation process, then it will be incorporated in the standards. Because many Indians, they don't participate in the standard, which I have seen personally. Even ORAN also, the open system, radio access network also, many we are not finding our institutes, except Indians who are working in the foreign companies, they are participating because of their company is forcing them to participate, provide the feedback. This we should realize, and we should, whoever is in the area, whichever interest area, relevant products, standard development, we must follow, is my advice only, you must follow. Then only your capability, visualization of the technology, the growth, and you can see by participating in the standardization. And if you contribute, that will be, certainly will make contribute if you have interest in the subject. So I think so. Anything more? Next page. This is the under quantum national mission planning. Mission plan, we have the targets to carry these tasks. This is one of the targets. I think next. I think so, last page. This is only whatever I spoken so far. Please mail me, or you can suggest, I can give suggestion. Whatever possible, it is to convey the meetings or anything. And we also, ITU, there are working groups, all chairman is under, from India side, from government of India, we are representing. So we encourage all you participate, and whatever membership is required, we will get it approval in our department. The focal point is there, where you get access the documents also. That will help a lot for you all. And other standards also, is possible, we will accommodate you to access the, especially startups and innovators, who are individually they can't access it. So we would like to, whatever possible, to help support and make part of innovation, in global innovation. And future we hope so India should also, as Atmanirbhar Bharat, should bring change from whatever not. We should expect that many people are finding dealing there in quantum also. Hope so something will come forward. The contribution in the standards as well as make a pathway for India to make a global supplier. I think so. Next, one more. We are connecting the workshop on Quantum Conclave, March 27-28. We are calling across the industry for India and also internet speakers. We expect that all the members who come here, please come and you convey all the members, and we will sit there and we will make a plan further how to go ahead. And quantum computing side, I think C-DAC, they can lead and we can sit there also. We can lead further, we can have a collaborative manner, we can work for towards it. That's we. Thank you for all, for patience.
Okay. Thank you, Dr. Chale, for a beautiful talk on standards and standards in progress for quantum technologies. So with this, this panel discussion comes to an end, and panel is open for questions. If there are any questions from audience, we can take on. Okay. So, okay. Thank you. On behalf of C-DAC, I thank all the panelists for sparing their valuable time. Thank you, sir.
Thank you, everyone. With this talk, we are coming to the end of the symposium. Now, I invite Ms. Anandita, Adjacent Scientist, C-DAC, on the dais to give the concluding remark.
Okay. Good evening, everyone. So I'm certain that the takeaways from this symposium will further deepen our thinking and stimulate our work in this direction. In my limited capacity and with the abundant support I have got and a great, great team to work with, I express my gratitude to all the speakers and the participants for their efforts. I understand it was a very short time given, and I'm very, very thankful. We all are very thankful. So please accept this on behalf of all the C-DACians. And I thought that it will be appropriate to summarize the ideas emanating from the symposium. We, which means the SICUCC members, the special interest group in quantum communication and computing, which is PAN-C-DAC. It has people from 12 centers in C-DAC. We made a humble effort and volunteered ourselves to understand the ecosystem, national and international. Then we tried to identify the potential stakeholders. Then we tried to reach out to them. Some were responded, some were not, and we are still hopeful. We look forward to. And we tried to bring everybody in a single platform. So when we were trying to look into this black box called quantum computing ecosystem, we found some potential processor technologies. We found algorithms that has to be looked into, that can be developed, that has to be implemented. We found error correction algorithms. We found software stack that has to be worked upon. We found hardware track, where apart from photonics and superconducting, we have other technologies, and something may come up in a year or two as well. Then we also understand that for anything scalable, there is a demand for indigenous development of control and hardware electronics. And I think from C-DAC, we are very much interested to collaborate on that aspect as well. We understand that the world, what is trending is actually HPC, QC, and CC environment. You have a quantum computer, you have an HPC, you have a cloud. So we are looking at that because I think C-DAC works with their user agencies. They are application oriented. So we'll be using them. We'll be buying them. So that was our motivation, and we tried our best. We have posed certain questions, and we look forward to the answers from everybody, and we are determined to do our best, and we look forward to your participation as well. Thank you.
Thank you, everyone. That will be the end of the symposium. Thank you so much.